data of histopathological analysis with a free fault intravenous injection of particles. Their maximum accumulation in the tumor tissue occurs. In general, during the accumulation of particles, no significant damage was observed in organs, tissue, and erythrocytes. It can be concluded that the studied particles do not cause pronounced toxic effects, and all the changes that occur on the background of the introduction are reversible and not persistent. Thank you for your attention.
Thank you very much. Time for one or two short questions, please.
Maybe I missed, but very shortly, what is the beneficial of using or converting nanoparticles in comparison with conventional photonetic therapy, with conventional photosensitizers?
Please.
Какие преимущества применения?
Я как не понял.
Low toxicity. And results of histological analysis.
The answer is given, you can discuss later. Further questions? If not, thank you again. And the coffee break has already started, but it will be shorter. Please assemble here in 20 minutes, not to shorten the lunch break. So we have to start at 11:30 sharp.
here. So, and my talk will be about the diffuse reflectance spectroscopy with self-calibrating probe. So in the introduction, I would like to say a couple of words about the diffuse reflectance measurements, which usually have the light source, the broadband light source, or the light source with several wavelengths, and the detector, which collects the diffusively scattered light propagated through biological tissue, and which are located at some distance from their source of light, and the diffuse light is described by their this simple equation from diffusion equation, diffusion approximation of light transport equation. And the attenuation of light is described with absorption and the reduced scattering coefficients, which both included in this equation. So, and while the reduced scattering spectra is quite monotonously decreased with the increasing of the wavelengths, so it has quite a simple shape. So their absorption coefficient of different chromophores have quite sophisticated spectrum with several peaks of different chromophores, and the main chromophores well known here as oxy and deoxyhemoglobin. It's water, melanin, lipids, and collagen. And by solving the inverse task, one can assess their concentrations of these chromophores from the registered diffuse spectrum. So blood content and blood saturation provides the information on hemodynamics and the blood oxygen supply and consumption of tissues. Water content can the information about the edema and other chromophores like bilirubin, melanin, collagen, etc. can also be useful for different diagnostic purposes. And there are a lot of applications of this method of diffuse optical spectroscopy, like brain hemodynamics, breast tumor margins, and treatment monitoring, assessment of different skin diseases, evaluating for scar severity, etc. However, there are some keys to successful reconstruction of tissue component composition from diffuse reflectance measurement. And the first issue is that the light transport model should be realistic enough to correctly describe light attenuation from source to detector, and there are some limitation of diffusion approximation in visible spectrum region and for small source detector distances because the diffusion approximation not work enough in this region, and usually some, for example, Monte Carlo simulation can be used to increase the accuracy of calculations in these parameters. And also, it is difficult to account for tissue scattering and absorption and homogeneity. We usually apply the homogeneity scattering and absorption model for describing the propagation of light here. Also, the reconstruction procedure should have a good convergence, and the more the number of unknowns, the less the convergence, and so that's why it is preferable to use wideband to include many different chromophores in the model and to increase the convergence of the reconstruction. And in my talk, I will concentrate on instrumental characteristics that should be taken into account during measurements. And instrumental perturbations such as variations of source spectral brightness, detector sensitivity, optical components, transient functions can lead to significant errors in the results of reconstruction. Also, it is well known that tissue inhomogeneity in the probe tissue interface is also critical for reconstruction of the tissue chromophores and can lead to significant errors. So there are several configurations of different diffuse reflectance measurement. The simplest one and the most popular, I think, is single source detector measurement. Usually it is made with a fiber source, single fiber source in the center, and several detection sources around, which are used for collection of diffuse scattered light. But in this case, some calibration procedure is needed to take into account the brightness of source and the sensitivity of the detector. So it is not a very robust method for diffuse reflectance measurement. Another approach, which is also very popular, is ratiometric approach, or single slope, when one source and two detectors are located on different distances from the source, and by using this ratio of two measurements in two detectors, one can exclude their source brightness and detector sensitivity from their instrumental. And however, not all transient characteristics of optical elements can be included with this approach. And the most robust approach is so-called self-calibration approach, or dual slope. It is known more than 20 years, but it's not taken enough attention in the literature for this method. And in this approach, at least two sources and two detectors should be used, and with each source, both measurements in both detectors should be provided. So by using this equation, one can exclude all transient characteristics in this method. So that's why it is called self-calibrating. So it doesn't need for any calibration system, so any fundamental measurements, to take into account all these parameters. The only thing that strictly have to be is the linearity of the detection system. Another beneficial of this approach is less sensitivity to the inhomogeneity of probe tissue interface. In the recent publication, I think, by Fantini group, they found that the area of sensitivity in the self-calibration approach is located deep in the tissue in comparison with single source detector and ratiometric approach, which is very close to the surface and increase maximum in the tissue probe interface. This is not very good because always on the surface of the tissue there are some optical inhomogeneity that leads to errors in the resulting in the reconstruction results. And they mainly use it for functional brain diagnostics, because it allows to exclude their hemodynamics in their skin of the head. And we, in our study, we have extended this research on the broadband and make this self-calibrating system with wideband from 400 to 1000 nanometer spectrum. So we have a broadband. I think it's the first application of this so wideband and for self-calibration approach. And in this work we compared their instrumental perturbations yielded in different source and detector channels and see the resistance to these perturbations in the single slope approach and in their self-calibration approach. So here is their experimental setup that we used. So the absorption spectrum model contains different chromophores like water, melanin, oxy and deoxyhemoglobin, and some dry matter, and the reduced scattering spectrum is more complex that used ordinary, has relay part and some, okay, in literature they call it misscattering, because so it is for the relay part is for small scatterers less than the wavelengths, and other part is for larger scatterers. And then we just minimize the discrepancy between the measured spectrum and the model spectrum. And here we made some experiments, tests on the resistance of the measurements to different instrumental perturbations. So the one simulates the losses in optical paths. So we, in fiber connections, optical switches, etc., by including a fiber with different diameter in the individual channel, and then we make some simulations of change of optical fiber position during measurements in real, so clinical situation, and we make it the ring from their from detection of source fiber and testing their inhomogeneity introduced in the probe tissue interface by including some absorber and this in this contact. And here are the results of calculation of extinction spectrum in with different inhomogeneity. And you can see that single slope approach have resistance to their inhomogeneity is introduced in the source channel. We can see that the spectrum doesn't change a lot here, but it doesn't have the resistance to the perturbation introduced to the detection channel, because the source is used twice in the measurement, but the detector, each detector used only single time. So this inhomogeneity can corrupt their spectrum quite a lot. And in the self-calibration approach, you can see that all measurement with perturbed with some perturbations introduced in individual channels have their resistance to these perturbations. And this was done on tissue fandom, and also we done these measurements on their tissue, on my hand, on a human palm, and we reconstructed their blood content, blood saturation, water content, and other parameters, and also scattering parameters. And you can see here the same situation, that their single slope measurements have resistance to their to the perturbation introduced in the source channel, but they don't have the immunity from the perturbation introduced to the detection channel, while our self-calibration approach is robust enough to exclude all perturbation in all channels. So it is produce quite stable data, and it's very important for the robust measurements to achieve the robust data from the reconstruction from the measurements. And in this slide, we made, I would like to show some preliminary results of application of this device, of this approach for monitoring of allografts and autografts of skin on a burn wound. So here's some preliminary results, but the idea is the following. If there is some burn wound, the best graft is the autograft, so taken from the patient. But if this area of the wound is quite large, it's not enough autografts, not enough this material, and some material from the donor can be taken to cover this burn wound. But in this case, there will be, after some period of time, there will be the rejection of this allograft due to immune reaction of the organism, but it's difficult to predict the time of rejection. And a doctor needs some method to monitor the state of allograft and to predict the rejection of this allograft. And there was a hypothesis of us that by monitoring the oxygen saturation, blood content, and water content, can predict this rejection. And here we find some differences in the state of blood content obtained in allografts and in autografts. We find it on the 6th day. You can see the differences, the big differences in oxygen saturation, and allografts has a lower oxygen saturation, probably due to the immune response, but their time of experiment was not enough high to see the real rejection after the monitoring. It was quite short, and we need some further investigation to see the rejection and to prove this hypothesis. So in conclusion, I would like to say that we have made some experimental setup for wideband diffuse reflectance measurement in visible and near-infrared, employing self-calibration procedure, and it was found that this device is enough robust for both instrumental perturbation introduced in individual channel and to some optical homogeneity introduced in probe tissue interface. And also there are earliest differences in blood and water content and tissue oxygenation were revealed between allografts and autografts of skin using this developed setup. And I would like to thank my colleagues from the Institute of Applied Physics and from Przewalski Research Medical University with the help with their experiments on rats and our funding. Thank you for your attention.
Thank you very much. Please, question.
Yeah, thank you for very interesting talk. My feeling is that if you provide pulse excitation and time resolve detection in this method, it allows you to provide something like 3D imaging. Why, if yes, why not to use in diffusion spectroscopy? Short pulse and time resolve detection. Because photons which have long path of reflection, etc., they need more time for detect and etc.
Thank you for your question. Unfortunately, it doesn't work in diffusion tomography. There are three methods of continuous wave, frequency modulation, and time resolved. Time resolved and frequency modulation provides information on scattering, so it allows to differentiate scattering and absorption, but it doesn't allow, and it helps a lot for reconstruction, because here we cannot discriminate these two values, but the broadband spectrum allows to approximate the reduced scattering with enough precision. But in frequency modulation and time resolved, you can describe it, discriminate it with quite high precision, and in time resolved, of course, with better precision. But it doesn't help you to go deeper in the tissue. The only way to go deeper is to use many source detection measurements located in different positions.
I did mention about more penetration, but differentiation of photons which are reflected near surface or more deeper. Because immediately the time of between excitation.
Yeah. You mean not their the depth resolution, but only discriminate. Yes. You can do this. Yeah. Of course. Of course.
Other question? Do you have points? And maybe, if I right understand, you recommend use two sources and two detectors.
Yes. This is more complex technique, of course, but the measurements are much more robust as the result.
And can you say some words about limitation of this scheme in compare with maybe other techniques? What do you think?
The first limitation is that it's longer in obtaining the results, but anyway, you can use several detectors at the same time. So you can decrease this limit. The second one is that you have to have very good linearity. This is actually not a big problem because you can calibrate your system with the linearity, and the good detectors have, spectrometers, for example, have this calibration curve, and they have very good linearity. And that's all.
Thank you again. Thank you very much.
Thank you.
I would like to invite next speaker. It is Dr. Krasnovsky is here. This is invited speaker. The title of the report. Time
Так, что нужно?
Так, который ваш? Это, да?
Красновский, где? Во, второй.
Вот это, да?
Спасибо.
Так, кликер, да, у вас?
Да, че, как его включать?
Все, он работает. Все.
Работает?
Нажимается на клавишу. Нет, на кликер, на сам. Вот, не получилось.
А,
Вот, клавиша вверх, надо стоит. Работает?
не,
Подождите. Все. Вот вниз нажимаете клавишу. Приемничек у него вот сюда.
ясно. Hello, I would like to thank organizer for invitation to present this talk. It is I planned when thought about this talk to present technical details, but I feel that probably потух.
Выдернули аккуратно. Все. Аккуратно провод не трогается.
That probably pure, naked technical detail, it will be too boring. Therefore, I decided to present the whole picture. Why these technical improvements were needed for the solution of what problems. And I start from the very beginning because I know for my own experience that not many people know in details what is singlet oxygen, how it was discovered. The very beginning, Fraunhofer lines were discovered in the beginning of 19th century, and two of these lines at 888 and 762 nanometer were especially bright. Better to say especially dark. So dark line is in the sun spectrum on the surface of, of Earth. Only 70 years later, the Russian physicist, St. Petersburg physicist Yegorov, managed to experimentally show that these two bands belong to light, absorption of light by oxygen of Earth's atmosphere, and belong to oxygen. So Yegorov is actually a founder of oxygen photonics. So it is surprising that nobody knows him presently. I remind about him at every talk which I present because it is very, very dishonest. We don't remember such a successful and careful scientist. He was rather famous before revolution, 1917, but then forgotten. Then many scientists repeated data of Yegorov's data, and to 1928, Robert Malekin provided explanation of why oxygen has this absorption. He applied to oxygen the molecular orbital theory and concluded that oxygen molecules has a triplet ground state and two excited singlet state. The 762 band, which was known at that time, due to Yegorov findings, he ascribed to transition from 0 to 1 sigma G state of oxygen, and he predicted also the existence of 1 delta G state with absorption band at about in infrared. This band was actually discovered in the spectrum atmosphere by Herzberg. Few years ago, it was really triumph of the molecular orbital theory. From that point, the term singlet oxygen appeared in spectroscopy and photochemistry as well. Yeah. Okay. Then very important data were reported by Hans Kautsky, Terenin, Alexander Nikolaevich Terenin, and Chris Foot, and they came to conclusion that singlet oxygen is produced due to energy transfer from triplet state of dyes, photosensitizer, to oxygen. So namely, 1 delta G oxygen, which Malekin's existence of Malekin, of which Malekin predicted, is a major part of this process. And this 1 delta G oxygen is capable of oxidation and destruction of many organic and biologically important compounds. Then a lot of paper followed in which it was shown that the photodynamic action, the process of destruction of cell of biological materials by light stained by different dyes, is due to mostly to singlet oxygen especially when we use porphyrins for destruction of cells. And then photodynamic therapy appears. Everybody knows about it. I won't explain. I only show the picture presented by Stranatka in his review, how he treated one of the carcinoma, I suppose. Very efficient method of treatment. So after this, it was clear that singlet oxygen is a very important particle in photochemistry, and photomedicine. And it is important to develop methods for detection and investigation of this particle. Many methods were proposed. Oh, yeah, sorry. Many methods were proposed, but I attract your attention to that method that we propose, our group. So we discovered that singlet oxygen can be detected in solution of photosensitizers by its own infrared phosphorescence at 1270 nanometers. This discovery was done using mechanical machines with mechanical phosphoroscope, which we built for detection of singlet oxygen, phosphorescence of chlorophyll, which was not known at that time. We successfully detected the phosphorescence of chlorophyll, and then I tried, maybe these machines can also detect singlet oxygen, and it was a full success. And this yellow picture in left corner shows why this experiment was successful, because we used photomultiplier FeO38, which has special spectral characteristic parameter. Besides the normal S1 spectral response, it also has additional infrared peak of sensitivity infrared exactly at 1270 nanometer, about that region. And the first paper in which this phosphorescence was described were shown on the previous slide, and these results, excitation spectra and emission spectra of this luminescence. You see that different pigments with different absorption bands sensitize this emission, and spectral all the time is the same, 1270 nanometers. So number 3, it is emission spectra and excitation, absorption spectra, different compounds which were used to excite it. And the second thing which was discovered at that time was that lifetime carbon tetrachloride in solvents where the lifetime of singlet oxygen is especially high, is about 30 milliseconds instead of 1 millisecond as was proposed previously. You see, this, of course, these papers increased interest to singlet oxygen detection very much. But the method we proposed for the first time was based on slow mechanical phosphoroscope with time resolution about minimum 0.1 millisecond. So it's very slow. It was interesting to increase the time resolution of the detecting systems. In Minsk, they first proposed use laser pulse lasers with short pulse of with nanosecond pulses to excite singlet oxygen. But I miss this paper, this paper of this Minsk group. So we and we transferred to another system, very advanced, which was proposed in our work in 1983. We managed to construct the spectrometer with laser excitation of dyes and time resolution photon counting system. It allowed us to measure the singlet oxygen decay in water and heavy water, and at the same time we measure decays and spectrum of emission. This work was attracted attention of the chair of nonlinear optics in Moscow University. So first, Valey Kamalov showed interest to this work, and then Nikolai Ivanovich Karateev and Sergei Alexandrovich Akhmanov too. They invited me. I presented several talks there at this chair, this department, and as a result, fantastic work was started where a lot of money was attracted to, and many bright, very excellent, really starring physicists were attracted to this work. And as a result, we made this spectrometer with nanosecond time resolution, which allowed us to measure the decays of singlet oxygen in water with the highest precision. Nobody, even now, at the present time, nobody can perform similar experiments. But simultaneously, we also assemble the same setup in Bach Institute of Biochemistry. And the first modification was done at about 1990. In the first modification of this setup, which we assembled there, was made using the nitrogen laser, which was acquired because of help of Mitrofan Fedorovich Steymach. It is, I'm very proud to say, he was at one of my lectures. I didn't know about that, and he proposed his help. As a result, we bought this nitrogen laser, which was very difficult to get in Soviet Union. Unfortunately, after this, these experiments stopped for a long time because of destruction of Soviet Union and total destruction everywhere. But at the West, the similar equipment was constructed only 7 years, in 1997, about 9 years later, in Japan by the firm Kamamatsu. So they managed to, but unfortunately we had 7 years luck fast, but these 7 years passed away without result because of total destruction. But this type of equipment is well known. It's very efficient for measurements in water, in living tissues, but it is not very useful for work, for example, in heavy water, in organic solvents, organic media, because it cannot measure the lifetime of singlet oxygen, which exceed, say, 20, 30 microseconds. And for the chemical and for the dynamic studies, it is often needed to measure this emission. And the first machine which I showed was phosphoroscope, couldn't measure decays. It only could measure the steady state equipment and estimate the lifetime. So it was very necessary to have new generation of equipment, and we assembled this new type of equipment only 3 years ago, in 2019. The block schema shown here on this slide. You know, for this machine we used the experience of all our spectrometers which we designed. And it is very efficient. So actually, what these machines, principles are the same. But for work with this machine, we use diode laser and modulated LED, light-emitting diodes. It is absolutely different things than the use of the lasers or short pulses. It works absolutely different. So we must, so far we don't know all the features of these machines, and working with them with great interest. But even at this stage of research, it allowed us to obtain surprising data, and a few of them, very few. I would like to show. This picture shows the decay kinetics of single oxygen luminescence in carbon tetrachloride. It is the same medium in which we discovered this emission for the first time. You see, we measured kinetics, it is exponential. Experimentally measured very easily with this machine. Then we noticed we can easily measure the quenching of singlet oxygen by triplet oxygen. This picture show and determine the rate constant is determined here. Of course, this is those who know the literature in this field know that Schmidt in Germany published similar data, but you know this Schmidt's data were obtained using spectrometer which couldn't measure decays. It is strange, but I cannot go into details. We notice a strange thing. The next, carotenoids. Everybody knows that carotenoids protect everything which protects photosynthetic organism used in cosmetics and so on for protection, because they quench triplet states of dyes, singlet oxygen, and don't produce singlet, triplet and singlet oxygen when excited directly. If you excite carotenoid by a laser, for example, carotenoids doesn't produce, it is triplets and singlet oxygen. It is a general belief. Using our machine, we showed that it is not right. This picture shows a quite recent result using as example of zeta-carotene, that under pulsed LED irradiation, it produces singlet oxygen luminescence with reasonable efficiency. It is not very high, about 1.5%, the quantum yield. But you see, the kinetics are here and are shown here on the picture. And the Stern-Former plot, which is on the right part of this picture, shows that it also, that zeta-carotene is also a strong quencher of singlet. So quench and photosensitize. It is new. Especially strong photosensitizer were found to be phytofluorine, the predecessor of zeta-carotene in biosynthesis. That's absolutely new information with all our previous setups which were used. It was impossible to measure. Only this type of design allowed to do it. Then another thing, you can excite oxygen. Oxygen has two singlet states. You can excite by laser 762 sigma-sigma transition in oxygen and obtain luminescence of singlet oxygen 1270. And this picture shows the action spectrum. You see both from Gofer-Yegorov light line from which I started are seen here. So you see we excite short wavelengths bands of oxygen and obtain luminescence at 1270. So it is very important for modeling the laser medical action of lasers, but I cannot stop on this problem in detail. And this picture shows the time resolved measurements of singlet oxygen luminescence after excitation of oxygen itself, which is dissolved in the same solvents, in certain solvents here. But as a result of this experiment, we managed to, it doesn't work. The light's line. Oh, we managed to obtain the absorption spectra of dissolved oxygen in air-saturated solvents. So it is oxygen which is dissolved everywhere because oxygen is present everywhere here. It was never, has never been done before our experiments. And you will see only two clear bands, absorption band 1273 and 760 nanometers in dissolved oxygen. In water, the band at 760 is relatively higher, but in principle, no difference, only two bands are seen. And two smaller bands at 690 and 1070 nanometers were also revealed in this experiment. So it is all that I wanted to show you. The development of technique of single oxygen detection is still promising, and it allows to reveal very interesting new properties of singlet oxygen, which are directly relevant to photobiology and photomedicine. Thank you.
Thank you very much for very interesting and deep report.
Alexander, how do your results impact the hypothetical model of light oxygen mechanism of low energy therapy in medicine?
Yeah, it's a very good question. We were working on this during last several years. I would like to say that this light oxygen mechanism works perfectly in model system, in solutions which contain certain amount of oxygen. But when we go to living structure, it doesn't work at all. At all, it doesn't work. So we have now very different results that it is not the case. So I know this when I report this data in medical audience, people start to protest, but it is true. Because why it doesn't work? Because the absorption coefficient of oxygen are so low that it is impossible to destroy something based on their excitation.
Even in 700
Yes.
nanometers.
In 700 you saw even smaller, the band is even smaller. So it doesn't work. But what works? I think that work water, because it absorbs in this region about 1,000 times more light energy. So it would be.
Maybe a therapeutic mechanism via water.
What I think so, because I don't see any other acceptors, and oxygen at this level, which of generation of singlet oxygen, is so low efficient, it's impossible to kill anything.
Thank you.
Very interesting. Other question? Good. Do we have some your means about a combination of concentration of the oxygen in water? How this concentration influence of activity of singlet oxygen?
You mean if we excite oxygen and water?
Yes.
That's the same thing. So it's very low efficient. And water, concentration of oxygen in water under normal condition is very low too. So in water it is impossible to find anything. What I see many people who report that they found things with oxygen under excitation, it surprised me. Because it was, they uses not direct message of it, but they use chemical acceptor or the different chemical method. But they are not very accurate to make a definite judgment.
Great.
We have some time. Thank you. Another question. You worked a lot on modification of the setups
Yeah,
to measure
Yeah.
the luminescence of same reduction. During the last few years, the film technique has been developed, fluorescence lifetime imaging. So do you think it can help in further studies of single upstream kinetics?
we now started a project, and one of the goals of it is to try it. But I don't believe that we will have success. And it's take a longer time, much time to explain this, but we will try. So experiment will show.
Thank you again.
Thank you very much.
Везде у нас внизу. У нас везде внизу. Ну, какие-то вот есть, посмотрите, посмотрите. А то, что вы подключите. Луис, Оливьер, да, есть, да. Что с ним делать?
Dear colleagues, next speaker is from Portugal, from Polytechnic Institute of Porto, Dr. Oliveira.
Yes, I'm here. Hello.
Can you hear me?
Can I share my presentation already?
Unfortunately,
Just a moment.
wait some time for technical solutions.
Okay.
Так, ничего не говорит, нет? Здесь нет.
Could you say something, Luis?
Yes, I'm here.
Do you hear us?
Yes.
Что-то из него плохо прилетает из него.
Hi, Luis. Do you hear us?
Yes, I can hear you perfectly. Just give me some moment because I'm trying
We
to
don't
share
hear
my
you yet.
presentation. Oh, sorry.
Алла, если может быть, ты скажешь. У нас без окон ходит. Ну, пока что динамика все есть, мы решили делать, что будет планироваться.
Hello, Luis. Can you hear us?
Yes. Yes, I can hear you.
Okay. We
Can
have
you
some.
hear me?
Yes, I can hear you, but on my personal laptop. Just wait a minute, please. We just solved the problem. With,
Okay, so I'm finding some problems on my side also because I'm trying to share my presentation and I cannot see it on the sharing screen.
I see. I see.
Слушай, скажи ему, что если не получится, сюда пришлет на e-mail кому-нибудь, можно будет загрузить, у компа показывать, если расшарить нельзя. В этом случае можно сюда
So
прислать.
just wait a minute, please. We will try to.
Yes, I will wait.
No problem.
Он не может расшарить экран. Как ему нужно расшарить? Он меня слышит, я с ним только что говорю.
Поэтому китайцы просят
Заранее.
заранее.
Luis?
Yes?
Luis, please say some words.
Sorry?
Hello, Luis.
Yes? Yes, can you hear me?
Just here. Okay.
Hello, can you hear me?
Он прикреплен.
Есть, да? Раз, два.
Попробуй там с микрофоном.
Luis? Can you hear us?
Yes? Yes, I can hear you.
You can hear. Yes, he can. Okay. Just we will try to make it.
Can you hear me?
Version. One. Whoa.
Вот теперь должно работать.
Попробуй. Luis?
Yes?
У нас есть небольшой запас, но из-за того, что первого нет.
Я думаю, все заняты пока с этим эфиром. Тут не кнопка, потому что программа очень такая крутая. Вчера проверяли, все нормально было, добился на точно. Сейчас все непонятно. Так, ну, все равно, почему пришел. все. Все завел на это. Что программе надо, что программе. Так, у него есть, да? Ну, нет, от него, видите, где-то.
Hello?
Andre, can you hear me?
Yes, I can hear you. Please, can say something.
Yes, I can hear you perfectly here on my side.
Yes. I think that it looks better on our side. We can try
Okay,
to
I
full
will
screen your
wait.
presentation.
No, 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 the same problem.
Okay.
Okay, I understand you are trying to save the problem.
Видимо, мой ноутбук хорошо срабатывает в этом случае, но просто в этот ноутбук воткнем, все будет хорошо.
Так, значит, китайцы, которые просят после последнего доклада перед обедом вот это делать не было завтра.
У нас звук отсюда не слышно, выводишь, у нас как это по-другому, короче, кабель Б отдается нам. Сейчас.
Он может развернуться, он может? На фуллскрин.
Several minutes, please. We don't know.
Okay, I will wait, no problem.
What's the problem.
I have time.
They try to solve that.
But Andre, please tell me, can you see already my presentation on your laptop?
Все верно. Вот. Так, давайте попробуем что-нибудь сказать.
Поздоровайтесь.
Hello.
Спасибо.
Вроде бы слышно, да?
Как включить?
Все, работает.
Some familiar faces.
Louis, please say something.
Yes, can you hear me now? Can you hear me? No, no. You cannot hear me.
Please say something again.
Yes, I was asking you if you can hear me now.
Он меня слышит, но мы его не слышим. Он все
No.
слышит, и мы
No.
там
Так, нам нужно только добавить, получается,
То есть это-
нам нужно только добавить
Can you hear me? So, Andre, you can
Yes,
hear
we
me,
can hear. I can hear you very perfectly.
but on your laptop, I understand. Okay, I understand.
только мы его отправляем так. Можно он еще раз? Я прошу прощения.
Please speak something again.
Yes, I am trying to speak to you, but you could not hear me before.
Может, здесь что-то оторвано?
Нет.
Can you hear me now? It's difficult. I will wait. Don't worry. So I saw Professor Tushin right now, but it disappeared.
достаточно громко будет.
Так. Сейчас. Нам нужно испробовать, нам нужно понять вообще, например, если музыку мы...
Ну, ребят, уже просто времени...
I can hear you now.
Понял, так, ну я думаю, что нужно, наверное, перезапуститься сейчас.
Ребят, выключайте микрофон. Нет, ничего не делайте, просто сделайте на весь экран, пускай с моего ноутбука говорит.
Хорошо, ладно.
Все, давайте, у нас времени просто.
Все, сделал.
Да, выключили?
Микрофон.
Нет, а мы с моего ноутбука.
А мы с моего ноутбука здесь на все будет слышно.
Вот здесь микрофон отключить.
Luis, can you hear me now? Luis, can you hear me?
Yes? Yes,
Yes,
sure.
okay.
Yes,
You
okay.
can
You
start-
can
Sound is
start
coming
your...
accurately.
Yes, we can hear
Yes, we can hear you now, and you can share your
presentation,
presentation, and you can start, I think.
Can you see already my presentation? And the diffusion properties and mobile water content as diagnostic parameters. Then we will pass to the materials and methods, where we will describe the preparation of kidney samples, both healthy and pathological, the preparation of glycerol and sucrose solutions, which were the probe molecules that we used in this study, and we will describe the methodology for the acquisition of collimated transmittance spectra and the thickness measuring setups that were used during treatments with the solutions that I mentioned. And then I will describe the calculation of the diffusion properties of glycerol and glucose molecules in kidney tissues. We will start the presentation of results by showing the kinetic spectroscopy and thickness measurements that we have obtained. Then we will make the data processing for the evaluation of the diffusion properties and identification of different diffusion properties and different mobile water content from the results between the healthy and the diseased kidney tissues. And then we will terminate our talk for today, showing the significance of the results for diagnostic purposes, the possibility of reproducing such a study with in vivo measurements, and future perspectives for the study of cancer progression. So, as you know, the evaluation of the diffusion of properties of some chemicals and agents is very important in different areas of activity, such as cryopreservation of organs and tissues, cosmetics and dermatology, clinical medicine, food preservation, and tissue optical clearing. So if we perform kinetic measurements using, for instance, the collimated transmittance setup and the diffuse reflectance setup, it is possible to evaluate the diffusion time of this agent, of these probe molecules in the biological tissues. In the situation that the tissues are ex vivo, we can use both approaches. But if the tissues are in vivo, we can use diffuse reflectance measurements, as was proven recently in a paper from my PhD student. When such measurements are made with various tissues, lots of tissues, under treatment with different concentrations of the probe molecules in water solutions, it is possible to obtain the mobile water content on the tissue that is under study. So the mobile water content is the group of free and weakly bound water. There are 4 states of water according to the binding strength to the other tissue components. But if we consider these 2, free and weakly bound water, they are considered or sometimes designated as mobile water content, which means that if we provide some action, some force on the tissues, this water can move from one place to the other and even to the outside of the tissue. The calculation of the diffusion coefficient can be made from the diffusion time if we have also kinetic thickness measurements, as we have already published in previous studies. Since the diffusion properties of the probe molecules and the mobile water content are different from the healthy and the diseased tissues, because we have proven this some years ago with colorectal cancer, we can use these parameters as diagnostic parameters. To contribute to this line of research, we decided to perform the present study, the study that I will present today, using not colorectal cancer as before, but now kidney cancer, designated as chromophobe renal cell carcinoma. So we will have studies or measurements made from healthy kidney and from chromophobe renal cell carcinoma tissues. So let's start describing the methodology. So human kidney fragments, as you can see from this picture on the left, from healthy areas and from chromophobe renal cell carcinoma areas were dissected from surgery, were retrieved from surgery at the Portuguese Oncology Institute, who cooperates with me in my research. These tissues were provided to us, and to prepare the samples for the spectroscopy and thickness measurements, we prepared the slices of tissues with a cryostat. So all samples, in total 110 healthy samples and 130 diseased samples were prepared for the present study, but all samples had approximated circular form with 1 centimeter in diameter. This is not too much important. What is important is that the samples had uniform thickness of half millimeter. This is a pre-established condition for the studies that we have performed. So the samples were the samples were prepared as needed for the studies and were kept in saline for 10 minutes before being submitted to measurements to keep their natural hydration. So the solutions were prepared in a simple manner. So we just mixed water and sugar or water with glycerol to prepare the various concentrations of the two solutions, of the two agents that we wanted to use. And the concentration was achieved and controlled by measuring the refractive index of the solution, which we already knew, at 20 degrees Celsius. So if you notice in this table on the bottom of this slide, these colored arrows indicate that the healthy tissues were only studied under treatment, under immersion, with solutions with concentrations of glycerol and sucrose equal or above 20%. For the diseased tissues, we used two additional concentrations, 15 and 10%, to get more accurate data on the results that we plan to obtain. The experimental setups were only these two that are presented here. So on the left, we see the collimated transmitter setup, which has a broadband lamp on the lower left, which delivers the beam through an optical fiber cable to the sample cuvette that you see on the center. There is first, there is a reduction of the beam to 3 millimeter diameter, and then a pinhole reduces the beam even more to 1 millimeter in diameter. So the sample is fixed inside this cuvette, and as you can see, the blue points around the sample are the solution. So the sample is immersed inside the cuvette in the solution, a large volume of the solution, at least 10 times more than the volume of the sample. And then the beam crosses the sample and the setup and goes through another optical fiber cable to the spectrometer to register the spectrum. So these measurements were made kinetically over time during the immersion, and we used an extent of 30 minutes to perform each particular study. And as a result, I present here a sample of studies. As you can see, the kinetics of the collimated transmittance spectrum of this particular tissue is moving and increasing smoothly over time of the immersion. So on the other hand, as I mentioned, we needed to make also kinetic measurements of the sample thickness, So to evaluate those kinetics, we inserted the sample inside two thin glasses with known thickness, dg, as you can see on this small equation. And we could measure also over time with the micrometer and calculate the kinetics of the sample thickness according to the equation that you are seeing right now. So as a result, you see on this graph, this is a typical measurement for these kinetics. And we started with 0.5 millimeter, if you remember from the previous slide. And then we see that this sample decreases drastically until 2-3 minutes, and then it starts to increase. So the blue circles that you see are the mean values with standard deviation with the bars, and we fitted this data with a smooth spline to show the time dependence of the sample thickness. So the calculations are very simple. As you can see, I will describe these two figures in a short time. So this is the kinetics of one collimated transmitter. So I'm talking about the top graph. So we measured the kinetics for different wavelengths, and we started on 600 nanometers. I will explain later why. And we ended at 800 nanometers. So representing the discrete time data for these wavelengths over time, we see that there is a smooth increase, a smooth exponential increase between the beginning of the treatment and 13 minutes of the treatment. So what we have done is that for this particular case, we trimmed the data and neglected all the data beyond 13 minutes for this particular treatment. It depends, the time of trimming depends on the concentration of the probe molecule in the solution that was used. In this case, it's 13 minutes. For other solutions, it can reach 30 minutes. It depends. We will see some cases of interest. So what we have done, considering each data set that was trimmed at 13 minutes on the top graph, we first displace this data set to have collimated transmittance equal to 0 at the beginning of the treatment, and then we normalize it to the highest value. And after performing this preparation of the data, you can see variations in the lower graph between 0 and 1 for all the data sets. They are not exactly equal, they are different in the central region, but after doing this, we can fit the discrete data with the equation that you see on the lower left of this slide to obtain tau. Tau is the characteristic diffusion time for this particular treatment. So as you can see already, there are 11 data sets, so we will make 11 fittings and we will obtain 11 tau values for each treatment. So after averaging and calculating the standard deviation for each particular treatment, we obtain a representation of the tau values as a function of the probe molecule concentration in the treating solution, as you can see on this top graph on the right. And if you fit it with a smooth spline and interpolate the data, you see that this curve has a peak, in this case, that you are seeing for a glycerol concentration of 35%. This is chromophore renal cell carcinoma. So if you go now to the thickness kinetic data on the bottom graph that you see, and you search on this curve for the time that corresponds to the tau value on the top, you will have the sample thickness at that particular time for this particular treatment, and you can use the lower equation on this slide to calculate the diffusion equation. So the problem is solved. Why? Because the top graph where we see the concentration of 35% is the maximum diffusion time, which corresponds to the unique diffusion of glycerol into the chromophobe renal cell carcinoma tissue in this case. So we will now move to the presentation of results, and now I will justify why we selected the range between 600 and 800 nanometers. As you can see, for both tissues, we have the mean collimated transmittance spectrum between 200 and 1000 nanometers for both cases. And you see that the range that we have selected, 600 to 800 nanometers, doesn't have any significant absorption bands, and it is almost linearly dependent on the wavelength. So this is a good range to do the kinetics and study the kinetics of the collimated transmittance, as we have done in the previous studies and also in this study that I am presenting at this time. So we will use only 3 graphs. We have lots of graphs like this for other treatments and other cases, but to make the presentation short, I selected to use only these 3 cases. So I'm talking about the healthy kidney treated with solutions containing 20% glycerol, 40% glycerol, and 60% glycerol to show the differences between these different concentrations, the effect that it produces on the healthy kidney in this case. So as you can see from the treatment with 20% glycerol, we have a small magnitude increase at the beginning of the treatment, considering the time scale, and then it saturates, and there is a small decrease on the collimated transmittance spectrum at later treatment. So this is a small magnitude transparency created in the kidney. So if you move to the treatment with 40% glycerol, we have higher magnitude variations, and as you can see, the increase is smooth between the beginning and the end of the treatment. So no trimming of this data in this particular treatment. On the other hand, if we move to higher concentrated solutions, as in the case of 60%, you see a strong increase at the beginning, and then it saturates. It doesn't grow any further above something like 8 to 10 minutes. It doesn't grow anymore, but then it starts to grow later on the treatment. Because these are mixed effects of water coming out and, in this case, glycerol going in. So we have to consider only the initial smooth exponential increase in every particular treatment. That's why we selected different trimming times for the data that we have considered. So similar graphs were made for the chromophobe renal cell carcinomas treated with glycerol also, and also with the treatments for both kinds of tissues with sucrose solutions. I will not present them here, but we were obtaining those graphs in this treatment. So considering the same treatments, you see now the kinetics of the collimated transmittance for the discrete wavelengths that we have selected. And as you can see, in the case of the treatment with 20% glycerol, the trimming time is 6 minutes. For 40%, as I previously referred, it goes further until 30 minutes. And for the treatment with 60% glycerol, it stops at 8 minutes. So we had to be careful about these times to trim the data in the appropriate time of treatment in each case. So after doing that, we performed the data processing that I have referred in the methodology. We decreased to 0% at the beginning, normalized to the highest value in each case, and here in these graphs you can see the data that can be fitted with the equation that you are seeing also right now, obtaining 11 tau values for each particular treatment. So at the end, and I'm almost finishing my presentation, we have obtained this data that you are seeing right here on these 2 tables. For the treatments with glycerol, as you can see, no treatments were made with 10% or 15% of glycerol on the healthy tissue. The 2 rows, the first 2 rows refer to the healthy kidney, and the two lower rows refer to the chromophobe renal cell carcinoma. You see the mean tau values that were obtained for each treatment and the corresponding standard deviation. The same is presented on the second table, but now for the treatments with sucrose solutions. And correspondingly to these tables, I have presented the data of tau as a function of the probe molecule concentration in the immersion solution. And as you can see, the first result that pops up to our eyes is that the healthy kidney has a maximum tau for concentration of 40%. In the opposite, the chromophobe renal cell carcinoma has the maximum tau at 30% concentration, both for glycerol and sucrose. This means that this difference shows that the healthy kidney has a mobile water content of 60% and the chromophobe renal cell carcinoma has 5% more of mobile water. So this is very important because I think we were the first to discover this in the case of colorectal cancer a few years ago, and now we can confirm from the kidney cancer that I'm presenting today, we can confirm with two probe molecules the same result, that the cancer, fully developed cancer in this case, shows that the tissues gain 5% more. So the bound water probably converted as cancer developed, the bound water was converted into mobile water. Why? Because cancer is growing and cancer needs more mobile water to transport nutrients for its development. So it makes sense. So this result is very important. And one of the studies that I plan to do in future, I'm planning this study for a long time, but I didn't have the tissues yet to do it, is to evaluate the mobile water content in different stages of cancer progression. It will be interesting to show that the peak in any of these two graphs will move to the right as we move from the healthy tissue to the fully developed cancer stage of any type of cancer. So other information that we have obtained is that the diffusion time, the characteristic diffusion time of glycerol and sucrose is also differentiated, as you can see from these green and red values on the lower center of this slide. So the probe molecules take different times to diffuse between the healthy tissue and the cancer tissue. So these two parameters, mobile water content and the diffusion time, can be considered as diagnostic parameters. So at the end, to calculate the diffusion coefficient and using the diffusion times that I just presented to you, we took the kinetic thickness variations, as you can see in both graphs here, and after calculating with the equation that I presented before, you also see that if you move from the healthy tissue, in any case, I'm talking about glycerol and sucrose, it's the same. So if you are using healthy tissue, you have some diffusion coefficient, and if you move to the cancer tissue, this value will decrease according to the equation. So this is very useful data for the discrimination of human kidney cancer. The difference between the diffusion time, diffusion coefficient, and also the mobile water content. So to conclude my presentation, the present study has demonstrated that the diffusion properties of probe molecules and the tissue water content, tissue mobile water content, there is a misprint there. Tissue mobile water content are differentiated between human healthy and chromophobe renal cell carcinoma kidney tissues and may be used for diagnostic purposes. And considering the analogy between the collimated transmittance and diffuse reflectance measurements, similar kinetic measurements may be performed in vivo. It will be interesting to study this in vivo. Why? Because while in the lab you have ex vivo tissues which are not connected to other tissues, in the situation of in vivo tissues, it will be somehow more complicated because of the water dynamics between adjacent tissues. The results will be different from what we have obtained in this case. So it is a situation that is very interesting to study, to reproduce the present study in vivo with in vivo tissues, but we expect that in that case, the results will be even different from the ones that we have obtained here. But as you know, due to ethic questions, it is not easy to perform such a study in vivo. The medical doctors will not allow us to do it. So we will try to find a way to make this study in vivo in cooperation with medical doctors somehow. We will try to do it in the future. So My suggestion is that similar studies to the ones that I presented here today should be done with other types of cancer tissues to perform the same evaluation. And the results obtained in the present study open the possibility of evaluating the same diagnostic parameters in different stages of cancer progression, as I already referred. I hope I have a meeting with the director of the Portuguese Oncology Institute, and I hope that he will provide the tissues from different stages of colorectal cancer for us to perform such a study. This is my plan, and I hope I will get lucky in this meeting next week with him. Let's see what he can tell me. So similar future studies can also be performed in tissues from patients under treatment procedures to monitor the efficiency of those treatments. So as you see from this graph that I prepared to present in this last slide, from the healthy tissue on the curve on the right to the curve on the left for cancer, we have to expect some variation. So tau increases and as cancer progresses, and the concentration of water will also increase according to the horizontal red arrow that I presented on top. So let's hope that we can fulfill this desire to perform these future studies, and it will bring very important information as I expect. So I conclude my presentation showing you some references that were used for this work and some grants that supported the student, my PhD student, and also Professor Tushin, who has collaborated with us with this study. And we thank you for your attention and hope that you have some interesting questions to present to us.
Luis, thank you very much. Dear colleagues, Luis, you hear me?
Yes, I can hear you.
Yes. Dr. Priyežev would like ask you.
Okay.
Hello? Hello?
Говорите.
Hi, Luis.
Hello, Professor
Thank you
Priyežev.
very much.
Pleasure to see you.
Thank you very much for your interesting talk. My question is, you focused on discussing the diffusion properties of different agents like glycerol by measuring the collimated transmission, diffusion, and reflection. Can is it possible to evaluate these results in terms of optical clearing of the tissues? Because glycerol is one of the optical clearing agents.
Very interesting question, but I think that you probably didn't notice. While I showed the graphs, I can show it once again. This creates transparency in the tissues. Let me just share once again the slide. This one in particular, if you consider this left graph, this is the treatment with 40% glycerol. As you can see, it is created some transparency in the tissue. In the others too, but this is the most beautiful graph that I had to show in this presentation. So this was done in the topic of creating transparency in the tissues.
Thank you. Thank you.
I finish this discussion because we lose some time for technical problems.
Okay, thank you again.
Luis, thank you very much.
Thank you, thank you, thank you, thank you.
Раз, раз, два. Раз, 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 раз. Сейчас я убавлю, сейчас чуть убавлю. Вот так вот, вот. Все.
Great.
Вот сюда презентацию нужно.
Good afternoon, dear colleagues. Do you hear me? Thank you for introducing me. It's a... А он, по идее, выключен. А вот вопрос.
Сейчас будем разбираться. Пробуйте еще раз. Есть?
Раз, раз. А так? А так нет. Okay, it's a great pleasure to take part in this conference and to present you our first results on the study of the influence of ionizing radiation, especially X-ray, on the scattering properties of the white matter of the brain. Radiation therapy is currently actively used as a component of the combined treatment of brain gliomas and is also used to treat intracranial metastasis of tumors of other localizations. In particular, during the treatment of glioblastoma, radiation therapy is recommended in almost all patients, except the cases where the functional status of the patient doesn't allow radiotherapy. Irradiation is performed after the surgical resection of the main tumorous mass and is aimed at destroying the residual tumor cells in the tumor bed. Currently, X-rays, gamma rays, and proton therapy are used to solve this task. And each of this type of radiation allow to slow down the tumor growth, but unfortunately often lead to a rising of functional deficit in the patient. The development of neurological deficit that occurs after radiation is often associated with damage to white matter pathways that are near the tumor focus and inevitably fallen into the radiation exposure zone. In addition to the formation of structural changes, formation of neurological deficit, I'm sorry, the structural changes also can cause difficulties in the subsequent treatment of patient for brain gliomas. For example, for patients with glioblastoma, tumor recurrence occurs in nearly all patients after the combined treatment, which follows the need to perform reoperation in such kind of patients, and these structural changes that were caused by ionizing radiation can cause some changes during the reoperation. I mean, in the cause some challenges in the finding the resection margin. Thus, the development of new methods that allow to detect structural changes in white matter that occur at different stages after the radiation procedure is of both fundamental and applied importance. On the one hand, it will allow to deeper understand some fundamental aspects of radiation-induced changes, and on the other hand, they will help to facilitate the search for the resection margin during reoperation after irradiation. So recently, a number of optical technologies have been actively developed that allow in vivo assessment of the biological tissue structure with minimal invasiveness and no need to use any additional contrast agents, where optical coherence tomography may be highlighted. OCT has already been demonstrated as a promising tool for brain tissue visualization, especially for tumorous, non-tumorous tissues margin detection. And due to the fact that myelinated nerve fibers that form the white matter of the brain have strong scattering properties, OCT maybe is a promising tool for precise white matter imaging. So we put forward an assumption that OCT is a promising tool for visualization of structural changes in white matter that appear after irradiation. Two groups of female Wistar rats aged from 20 to 14 weeks were prepared for the study. The control group animals from the control group were once anesthetized using medetomidine, and the experimental animals had the same anesthesia and then underwent the X-ray irradiation of the right hemisphere of the brain at a dose of 15 gray at a dose rate 0.7 gray per minute. To prevent irradiation of other parts of the experiment animal, all rats were covered with a lead apron. At 7 time points from the irradiation procedure, from 2 to 14 weeks, 5 irradiated and 3 control animals were euthanized with the following brain extraction from the cranial cavity, and then the ex vivo based specimens were forwarded to OCT and immunohistochemical study. OCT study was performed using a multimodal optical coherence tomography device that was developed in the Institute of Applied Physics in Nizhny Novgorod, Russia. The technical features of the used device can be seen on the screen. And the entire surface of the fresh frontal sections of the brain specimens were subjected to OCT study. The images were collected in the contactless mode through several strips with a 2 millimeter step, which allowed us to have an overlap between the adjacent image that was necessary for subsequent merging. The quantitative assessment of OCT data was performed through calculation of attenuation coefficient. That is the most commonly used parameter for OCT numerical processing. We calculated the attenuation coefficient values in the depth range from 120 to 300 microns of the depth of the OCT image. And then we built in-phase color-coded maps from each OCT image. And in addition to building color-coded maps, we also used the median value of the attenuation coefficient on each OCT image. For this part, we since the size of the white matter structures is smaller than the entire OCT image, we used the special algorithm that allow us to calculate the attenuation coefficient in a manually selected region of the OCT image. After the OCT imaging, each brain section was subjected to immunohistochemical study using the antibodies against the myelin basic proteins, and all the histological sections were visually analyzed by a pathologist using light microscopy. So let us move to the results. The first stage of the work included the selection of a region of interest in order to targeted study the morphology and scattering properties of a particular white matter structure. The general review of IHC images and optical maps allowed us to visualize several white matter structures, but we made a decision to choose only one structure, namely the corpus callosum, as a region of interest. And this was dictated by three main reasons. The possibility of a targeted study of this structure on all histological section, the larger size of the corpus callosum in comparison with other white matter structures, and the convenience of post-processing of the OCT data. Histologically, the normal corpus callosum is characterized by presence of a large number of densely packed and ordered myelinated fibers. However, structural changes in this area, in the experimental animals were found at 3 time points, at 2, 6, and 12 weeks after radiation. It's interesting to note that structural changes were found at 2 weeks in only the area of irradiated hemisphere, while at the time points corresponding to 6 and 12 weeks, we found some damage both in the irradiated and the contralateral hemisphere. So, 2 weeks after radiation, a mild white matter edema was found in the corpus callosum. That was, as I already said, located in the irradiated hemisphere, and was characterized by presence, by increasing in the size and number of spaces between myelinated fibers. The structure of myelinated fibers themselves, however, didn't change, so we didn't find any damage or demyelination of the fibers, and observed changes are reversible, which was confirmed by their disappearance by 4 weeks after radiation. The next appearance of structural changes in the corpus callosum was noted at the 6 weeks after radiation. At this stage, the changes have already the changes have already affected both hemispheres. We also found the edema, which was more severe in comparison with the 2 week standpoint, and at the stage of 12 weeks, we also found this kind of edema. It's interesting to say that the occurrence of edema in the contralateral hemisphere indicates the possibility of spreading the damage to the contralateral hemisphere that was not exposed to ionizing radiation, and the damage is spreading along the myelinated fibers. At other time points, namely the 8, 10, and 14 weeks, we didn't find any changes in the corpus callosum structure. A comparative analysis of attenuation coefficient changes in the corpus callosum obtained from different time points from the irradiation revealed the same trend as in the study of structural properties. So at the stage of 2 weeks, we recorded a statistical significant decrease in attenuation coefficient values in the irradiated hemisphere in comparison with both with the control group and contralateral hemisphere. These changes were reversible, so at the 4 weeks after radiation, there was a return of attenuation coefficient values to normal values. Then, at the stages of 6 and 12 weeks after radiation, the attenuation coefficient values decreased both in the area of irradiated hemisphere and in the area of contralateral hemisphere. And you can clearly visualize these changes on the color-coded maps, where these damaged areas are characterized by predominance of intermediate colors, namely the green, yellow, and blue. At all other time points, no differences were found in the attenuation coefficient values between the control and experimental group. And we also may see it on presented attenuation color-coded maps. So, summarizing the speech, I would like to say that we discovered acute and early delayed morphological changes in the corpus callosum arising after exposure to ionizing radiation that were characterized by the decrease in the attenuation coefficient values. Both stages were marked by occurrence of reversible edema of white matter. And it was noted that at the stage of acute injuries, 2 weeks after radiation, the edema was found only in the radiated hemisphere, while at the stage of early delayed images, the edema affected both irradiated and the contralateral hemisphere. Thus, OCT may be a promising tool for detection of radiation-induced changes. And I would also like to say that this work is in progress. The experiment is progress, and since we didn't find any damage to myelinated fibers, we suppose that this damage will occur after a longer period of time, for example, 6 months, and so actually the next month we will see if it works. I would like also to thank all my team that took part in the study, and also the Russian Science Foundation for financial support, and of course the audience for your attention. Thank you.
Thank you, Ksenia, for a very nice presentation. And actually, my question is about the origin of the decrease of attenuation coefficient in your experiment. First of all, I would like to ask, do you separate scattering and absorption in the attenuation coefficient? Yeah, because both scattering and absorption contribute to this coefficient. This is the first, and then what is the mechanism of decreasing attenuation coefficient? Is it just because of the edema, or there are some other mechanisms?
Thank you for your question. No, actually, we don't divide the attenuation into the scattering and the absorption. But as I know, the scattering is has the most influence to the OCT signal, especially in brain. So, if we are speaking about the second question, as I understand, the main mechanisms of slowing down the value of attenuation coefficient is that the concentration of the scatterers, the main scatterers in the tissue, becomes a bit lower, if I can say that, because of edema. Yeah.
Okay, so edema is the main mechanism.
Yep.
Okay, great. Thank you.
You're welcome.
Speak some words about time needs for measurement of attenuation. It's second, hours, or milliseconds. How long?
Thank you for your question. Actually, the time of obtaining our 3D OCT image is for 26 seconds, and the quantitative assessment can be performed almost in real time. But unfortunately, now we can't. So we need to use the separate programs for obtaining the OCT image and for numerical processing. And now we're working on the topic to to make one program that will carry out all the work in the same time.
But what do you think this time influence of results of your measurements or not?
Thank you for the question. No, we actually we have carried out several experiments concerning the time influence of the scattering properties of tissue samples, and we didn't find any statistically significant influence on the optical properties of the exhibitive specimen.
Thank you very much.
You're welcome.
Вот, все, да, на стаджере.
张老师，您在吗？张，他好像听不见我说。
Yes, here I'm Junzhang. I can. Yes, I can hear you. I can hear you. Can you hear me? Yes, this is Junzhang. I can hear you. Hello, hello, hello.
Hello.
Yes, yes, yes. I can hear you. Hello.
Андрей, я здесь. Ну, что, привет, привет большой всем. Слышно меня? Привет большой всем. Ты меня слышишь? Нет? Слышно хорошо? Ну, я громко говорил. Плохо, да? Я вас хорошо слышу. Ага. Да, но вот разобрались, как это грузить-то слайды. Чтоб завтра сбоев не было. Андрей, к сожалению, я должен бежать на занятие. Все, тогда я появлюсь туда к началу следующей сессии. Постараюсь успеть. Давай, все. Ребят, все отлично идет. Спасибо.
Yeah, please let us know how to share screen. Yeah. Yeah. Yes, I'm here. Yes, I'm here. I'm ready. Oh yes, I saw a lot of slides here, from number 1 to number 15. But I'm wondering, should I upload my presentation first? Okay, let me check. Which one is screen share? Look. Yeah, welcome to Bluebird. Yeah, I see that. Yes. And where's oh yes, I see that. I saw that. Okay. Yeah, let me try. But no effect. No effect. Oh, sure. Yes. Yeah, I one more time, but still no effect. I saw this a lot of like a chat, web camera, audio, breakout rooms. Yeah, screen share, but I clicked the no effect. Look. Yeah. One more time, right? That's yes, but under the screen share button, there's some like for more information, visit like a website, and under that there's a lot of under that it's like a mini how ask me to choose the slides from number 1 to number 15. Blue button. Okay, let me check that blue button. Oh, okay, that's Yeah, that's oh, let me take a. Yeah, that's let me take a look. That's the third one, right? Third one. Oh, I look. Oh, yeah, I saw that. Let me try. Okay. And that's yeah, I think looks it works. Maybe. Oh yes. 1 minute. 1 minute. 1 minute. That's it's good. Can you see that? Perfect, right? That's can you see the? Can you? Yeah, currently is a full screen. Good.
张老师，您放映一下。
Oh, okay. Let me try. Yes, I'm now playing. I will choose the demo mode. This looks it's a mode in problem. Okay. Yes. Full screen. F5. Yes, let me try. Currently, I'm a full screen. Okay. No. Yes, I. Wait a minute. You can see this. Yes. Wait a minute. Wait. Okay, that's demonstration. Yes. No. Let me try to another window. Okay. Another window. Yeah, full screen. Or maybe the full screen. Okay. Let me. How about this? It's good. It's good. Okay, perfect. Good. Okay, thank you. Okay, that's good. So oh, I'm sorry. Our current don't have camera in this desktop. I'm sorry. Yeah. So thank you. So it's good. Okay. Sure. So.
Yeah. Hello. Yeah. Great. So can you? Yeah, nice. Okay, I'll try to share. Can see. It's okay. You see. Okay, let me try this one. So can it work well?
Professor Liu Zhiyi.
Okay, I will stop share.
Professor Andrew is not here. Professor Liu Zhiyi. Professor Liu Zhiyi, please. I think. Oh.
Hello, hello. Can you hear me? Hello. Okay, okay. Okay, okay. I'm finding my point. Okay, can you hear my? And I'm sharing my screen. Okay, okay, okay. And can you see my point? Okay, okay. Thank you. Thank you. Okay, okay. Hello, hello. Yeah, hello. Okay, okay. Thank you.
I would like to test. I would like to help TTYU. I will help Professor Danju to test her PowerPoint. Yes, wait for a minute. Can you see my screen?
No, test.
Can you see the change of the slices?
No, test.
Okay. Perfect, thank you.
Okay, okay, it's okay, it's okay. 需要给到你们权限。
Hello. Me? Okay, thank you. I think the other people yeah. Yeah, TTYU and Tingtingyu is the same person. I think we can finish this testing, and maybe the other participants have some other things. I will tell them about the
挺好玩。And can you see my PowerPoint? Can you see my PowerPoint?
I see. Okay. Yeah. Okay. Thank you. See you tomorrow. See you. Thank you so much. Bye. Bye.
Hello. And close on the PowerPoint. Thank you. Okay.
давай. Вот так вот. Да, пожалуйста. Можно?
Да, все, микрофон, так микрофон разговаривает, чтобы вас. Могу так подать, кому удобно.
Нормально. Dear colleagues, my name is Andrei Belikov. I am from St. Petersburg. I am employer of ITMO University and First Medical State University too. The title of my report is Physical Features of Laser Multiwave Action on Biological Tissues. And this research was supported by Russian Science Foundation. Number of the project you can see here. In my report, in my report, I will speak about motivation for multi-wave laser action, and also I discuss about peculiarities of multi-wave laser action in neurosurgery, dermatology for drug delivery and photodynamic treatment of mucosis, and in dermatology too for treatment of telangiectasia. These topics correspond with activity of my lab in the ITMO University. Some words about motivation for multi-wave laser action. First of all, the reason is increasing the efficiency of action to biotissue of laser radiation with one wavelength due to the action of laser radiation with another wavelength. In similar, the biotissue can be divided on target and surrounding tissue, and you speak about target, we can tell about cells, vessels, tumors, and other. If speak about surrounding tissue, you can see it can be interstitial fluid, muscles, and others. The pictures represent these two conditions. You can see here on the right side of the slide. The multi-wave laser action can be divided on two types. First type is laser radiation, when laser radiation with wavelength lambda 1 act on the tissue surrounding the target and change its property or condition in such a way that the interaction with the target of radiation with the wavelength lambda 2 is more efficient. If speak about second type of action, you can see it action on the surrounding tissue, and during this action you can change the target too. First of all, some words about multi-wave laser action in neurosurgery, and very popular method in neurosurgery for dual wave surgery, for dual wave surgery system to resect brain tumor or are very promising. In this system, we have two wavelengths. One it's thulmium laser, and another is ytterbium laser, or another is ytterbium laser, which applied before, after, during action of erbium laser, which used for cutting of the brain tissue. Here you can see the results of compare of the results of combined action on the cortical tissue of the mouse with different laser, with different combination of laser. First combination, it is ytterbium plus erbium YAG laser, and other combination is thulium with erbium laser. And here you can see on the right side of the slide, you can see the histology picture, and you can see that for these two different type, the thermal injury is different. For example, after ytterbium plus erbium laser radiation, the thermal injury much more less than after thulium plus erbium laser radiation. And so we can conclude that ytterbium plus erbium dual wavelength laser system can effectively resect neural tissue with high localization. The other topic of my report is the possibility of multi-wave laser action in dermatology. And in our lab, we investigate application of the light system for treatment of mucosis. Mucosis, as you see, is infection, disease caused by parasitic fungi. And incidence of mucosis is 50 to 20% of population. In the mass media, usually speak about onychomycosis, which is the infection disease of the nail caused by various type of parasitic fungi. The incidence of this disease is 5.5% of population, and in the 5 to 10% of cases of onychomycosis, the reason of this disease is Candida albicans. It is the type of fungi. For multi-wave laser treatment of onychomycosis, we can use three types of laser wavelengths. First wavelength, it is laser wavelengths for microapparition of the nail, because the nail is a high barrier for penetration any drug into the under the nail plate. First of all, needs micropore. And second wavelength needs for deliver of the drug under the nail plate. And the third wave, in the case of photodynamic treatment, this wavelength needs for activation of photodynamic processes. And if look on the choice laser wavelength for microapparition of the nail plate, need look on the absorption coefficients of the nail or water, and for effective nail microapparition needs that wavelength corresponds with the absorption peak of the water or with the nail. You can see for this reason, for microapparition, very perspective used erbium lasers, which high absorb in the nail plate. If speak about selective microapparition, need to look in the visible range. There is the nail plate more have more absorbance than the water. In this range, in the nail, absorbed keratin and other, and also the pathogens of the fungi, which is the reason of onychomycosis. For this reason, for microapparition can be used semiconductor lasers, which wavelength represents on the left side of the graph. for the drug delivery, for the drug delivery needs choose the valent which is not absorbed in the drug, because during the delivery the properties of the drug can be changed. But vice versa, for photodynamic treatment need applicate the wavelengths which have big absorb in the drug. For this reason, for photoactivation of the photodynamic drug can be used this three type of light wavelengths. The process of the microporation and drug delivery can be divided on two types. First type is direct. It is when after inspection, first of all we make microporation. After that, put the drug on the surface of the nail, and after that deliver the drug under the nail plate, and after that produce photodynamic treatment. If speak another type, is not direct method. In this method, after inspection, we applied the drug on the nail plate, and after that make microporation and delivery through the layer of the drug. If speak about ergonomic on this technology, on ergonomic point of view, the non-direct method more simple and from ergonomical more better. I don't speak about the technology or about the our research for optimization of the laser parameter for microporation and delivery. The combination of this parameter, its optimal parameter for microporation and delivery under the nail plate and skin represent here. But the open question was which wavelengths can be used for on the last stage of technology on photodynamic or PDT stage. In the stage we compare these three wavelengths, and I would like to represent the results of our study. First of all, we calculate the singlet oxygen yield according to equation represented here, and we determine what the wavelengths with 105 nanometers have higher singlet oxygen yield. You can see in the table, and the singlet oxygen yield depends from the power of the laser radiation. So the leader of the singlet oxygen production is wavelength 405 nanometers. And after that, we start with fungi. For our investigation, we prepare special medium, which called Sabura medium. This equipment for this stage represent here. On the output of this activity, we have the Petri dish with the Sabura medium, which contain the fungi inside. And here represents the stage, the scheme and stage of our research. First of all, we placed of paper shield with hole on Sabura medium surface, and after that place tissue, in our case it was nail plate or chicken skin, over the hole in paper shield, and after that make direct or non-direct microporation and delivery aqueous suspension of two different PDT agent. First agent it is Haloderm. This chlorine-contained drug, and other drug was named chlorine with hyaluronic acid, which is used for PDT approval of the PDT approval of the properties of the skin in cosmetology. And after that we make PDT treatment with different wavelengths. The parameters for PDT treatments which was optimal because it was maximal energy density and maximal dose without produce erythema on the skin. It is a limitation for this technology. And after that we remove nail plate or chicken skin and produced 24 hours incubation and with temperature plus 37 degrees of Celsius. After incubation, we put the sample under the optical microscope and calculate the quantity of colonial foundation unit, CFU, per square millimeters. Colonial foundation units, it is a characterization of the fungi. This on the slide you can see the photos of the Sabura medium after the PDT treatment of the sample with different wavelengths. And first of all, you can see that the dimension of the CFU differ for nail plate or skin. And if you look in the bigger photograph, you can see the CFUs, it's spheres. It is particle of the fungi. And you can see that in the treated, you can see this CFUs around the treated area, and inside the treated area, this colonial foundation unit is absent. And if speak about the results of our experiment, you can see that the CFU per square millimeters depends from the type of microporation and delivery, and depends from wavelength of the PDT light. And you can see that the fungistatic effect when the CFU per square millimeter equal 0. We observed only after direct nail plate microporation, but in this case we not observed differ between the wavelengths. But if speak about the skin, we for the skin we have fungistatic effect only after direct microaspiration and delivery, and only after PTC treatment with wavelengths 0.5 nanometers. And as conclude for this part of the experiment, we suggest use direct microaspiration and delivery method and use wavelengths 405 nanometers for photodynamic activation. I am conclude because I have the next stage of my report, but we have no time, and okay, and I am finished and ready for your answer.
Thank you for the very interesting presentation. Actually, I have a very small question. I missed what was the purpose of using the laser at 3 microns?
We use the general idea, first of all, microparate the nail, or microparate the...
Okay, so it was used for
Yes, for microaspiration.
Okay. Thank you.
Because the wavelengths of this radiation shift under the absorption peak of the drug.
I really didn't understand, but you said that when we use porphyrin sensitizer, 405 nanometers was the most efficient.
No. We have chlorine contained. Chlorine contained.
And why this wavelength is most efficient?
The chlorine E6, its activator in this drug, have some peak of absorption. You can see here, first, this is spectrum of absorption of the chlorine-containing drug which we use. We have one band here, second here, and third here. But typically for PDT treatment, use this wavelength because speed that needs that laser light radiation deeper penetrate in the skin and other. And in this reason, use this wavelength. But it speak about onychomycosis, which and for onychomycosis we have nail which not scattering media in compare with the skin, and this nail have transparent in the UV region, and in this region we can try to use this and this wavelengths and compare. As results, we determine that they are more efficient for this wavelength.
Is it important that it is dynamic, so it is not monomeric guys? It has two peaks.
It's not monomeric. Yeah. No.
But why did you use monomeric guys? Monomeric are more efficient.
Maybe it's a discussion, maybe later.
We have maybe three papers about this, and of course I maybe explain it. It's not simple answer.
Thank you.
Thank you. Thank you. Dear colleagues, we have only 20 minutes before invited talks. Please go to next talk. Is entitled as experimental substation of the prospects for the use of blue laser 450 nanometers for
Good afternoon, dear listeners. My name is Chernyshov. I'm pediatric surgeon, and theme of my speech, experimental substitution of the prospects for the use of blue laser radiation for the effective removal of congenital giant pigment nevi. Congenital giant pigmented nevi are melanocytic formation of the skin, mainly black-brown in color, occupying relatively large surfaces of the skin, often with hair. Forms of nevi for primary proliferation of melanocytes in the skin, epidermal, intradermal, and intrasubdermal. In accordance with the classification of pigmented nevi, according to size, they are divided into gigantic, medium, and small. During the life of a child, the stage of relatively sharp increase in giant pigmented nevi are not, more often at the age of 4 and 7 years, and especially during the period of hormonal adjustment. Traumatic damage to the pigmented nevi by clothing and household items, excessive insulation can lead fragmentation and of the surface, inflammation, and the bleeding. In the adult period, to malignancy. Psychological and social problems. Examples of various forms. Giant small, medium, and gigantic. Today there are many methods of the treatment, like method of cryodestruction, diathermal coagulation, surgical method of treatment, carbon dioxide dermabrasion, but the frequency of unsatisfactory results and recurrence of nevi with these methods range from 6 to 41% of causes. Thus, it is obvious that there is an emerging problem of effective treatment of giant pigmented nevi in children. Currently, laser methods that provide maximum therapeutic effect are considered the most promising and precision method. The essence of proposed method is that the effect on pigmented tissues is carried by laser radiation with a wavelength of 450 nanometer, having selective absorption mainly by melanin and oxyhemoglobin to a laser excited by water. We can see this on the absorption spectrum. That provides a predictable layer-by-layer removal of pigmented tissues and minimizes damage to the tissue structure subject to them, including the elements of the skin appendages located there. The purpose of the work is to improve the results of the treatment of giant pigmented nevi by using blue laser radiation to remove this pigmented formation in children. We have priority of the invention of a method of treatment dated July 14, 2023. The laser medical semiconductor device laser mid was used in the work and developed by Russian engineer club in Tula. Biomedical research in vitro and in vivo on model biological objects, tissues of chilled samples, liver and muscles, mini pigs, skin tissues of living pigmented laboratory rats. In experimental study, used laser radiation with 450 nanometers in continuous and pulsed mode with constant and variable parameters. Pulse repetition frequency of
50 hertz, pulse duration of half second, diameter of 1 millimeter of laser spot, scanning speed of 1 centimeter a second, one pass over the surface with overlap of laser spots on 1/4 of the area, and variable parameters of power and time between pulses. Biomedical experimental study in vitro to study the characteristics of the impact on the tissues of chilled samples of pig liver and muscles. On liver, in continuous mode, we can see a more pronounced impact with an increase in power. In pulse mode, coagulation effect is more superficial, without crater formation. In continuous mode, the histological picture is presented by the formation of crater with an increase in power, but with a depth of no more 280 microns. In pulse mode, the histological picture is presented without the formation of the craters with a clear zone of coagulation necrosis. The depth of exposure does not differ. Blue laser radiation has predicted relatively shallow thermal damage to biological tissues from 200 microns to 450 microns in proportion to the increase in power. The use of pulse mode of blue laser radiation formed more superficial thermal damage without the formation of craters defects compared to continuous mode. The use of continuous blue radiation ensures the formation of shallow crater defects only with a significant increase in power. Recommended parameters of the blue laser radiation mode: power of 3 watt and 10 watt, pulse duration of half second, the period between pulse of half second. Thus, the analysis of the result of the in vitro study noted by the peculiarities of exposure and determined the promising parameters of blue laser radiation for the process of layer by layer removal and excision of pigmented structures of the skin. An in vitro experimental part of the study, the features of damage and regeneration process on the pigmented skin of back of a liver laboratory rat. A view with exposure zones on depilated back. Different modes. Schematic drawing of areas of damage. Normal skin structure, skin with impact zone with 3 watt power, with zone of coagulation and zone of coagulation with power 10 watt. Histomorphological assessment of the effect on the skin of a laboratory rat in continuous mode. We can see an increase in the depth of coagulation necrosis is observed with a significant increase in power to up to 850 microns. In pulsed mode, with an increase in power, coagulation necrosis is more pronounced, but an increase in the depth is not observed. On 12 days, we can see the impact zone is made by restored epidermis. On 90 days, the impact zone is made by restored epidermis and evenly parallel collagen. The structure of the skin is preserved, including appendages. The firm method provides a reduction of traumatic damage to tissue structure in operating area due to selective destructive effect on pigmented tissues, radical precision removal of them, minimal damage to the underlying tissues, partial preservation of the proximal area of the skin appendages. Healing regeneration of the wound surface due to central epithelialization. The choice of the power parameters should be carried taking into account the age characteristics of patient groups. The indicated position will be contribute the improvement and the reduction of the duration of the treatment of giant pigmented nevi in children in order to achieve a good clinical and aesthetic result. An experimental study determined the optimal parameters of blue laser radiation for the effective removal of various forms in children, and an experimental model of the method was formed. The parameters of this laser radiation recommended for use in clinical study in pediatric patients. Constant parameters: pulse repetition of 1 Hertz, pulse duration of half second, time between pulse of half second, diameter of 1 millimeter laser spot, scanning speed of 1 centimeter on second, one pass over the surface with overlap of laser spots by 1/4 of the eye area. Variable parameters taking into account the age of groups patients and different of power. In our clinic, blue laser radiation for the treatment of various forms was used in 20 children. All 20 patients underwent the necessary diagnostic tests before surgical treatment. In this slide, ultrasound examination is the core Doppler mapping, determination of size and depth of giant pigment nevi at speed of blood flow. Examples of dermatoscopy, predestination benign pre or malignant nature of pigmented nevi. Clinical research, a method of treating with blue laser radiation. The form method takes into account the morphological structure of the giant pigment nevi and the age characteristics of the skin of children patients. The method includes 2 main positions for removal: layer by layer, removal of pigmented tissues, and excision of individual structural elements. Technical implementation: excision of individual structural elements. Tissue direction is carried along the circumference and a distance of at least 0.1 millimeter from the each of element to the entire depth of its location. On this table we can see laser radiation power modes recommended for removal by excision individual structural elements. The layer by layer removal of pigmented tissues is carried by laser radiation with wavelength 450 nanometers as follows. The end of manipulator is positioned perpendicular and almost in contact and a distance of no more than 0.1 millimeters to the surface of the affected object. A laser spot with a diameter of 1 millimeters with a scanning speed of 1 centimeters on second. By sequential movement and overlap on 1/4 of the spot area and with one pass on the surface of the pigment formation. Laser on this table we can see laser radiation power mode recommended by layer for layer by layer removal. The results of treatment of giant pigment nevi in children. The immediate and long-term period proceeded without complications. Healing of the wound surface was not on average for 14 days. Contour examination we carried on 7 days, 14 and 30. Echotemnesis up to years. There were no complications during treatment. Satisfactory results of treatment we note in all patients, including 8 children at stage of treatment. We have a good final clinical result in 12 children, satisfactory at 8 children, and don't have a bad result. Example, child with congenital giant pigmented nevus in back area. A general view before surgery, 2 molds layer by layer removal on A, B with power 6 watt, excision of individual elements C and D with power 6 and 10 watt. The results at the treatment stage on after 3 months and 0 day. And the result in 6 months. Congenital giant pigmented nevus in the area of the left 6. General view and the results at the treatment stage on 6 months after exposure and immediately after exposure. This layer by layer removal with power 10 watt. Example 3 congenital giant pigmented nevus in forehead. General view and the result after 2 stages of treatment, after 6 months and after 1 month. And this the etap. Congenital giant small pigmented nevus in the area of the left cheek. General view and the result after 6 months. And patients with giant medium pigmented nevus in the area of the right shin, general view and the result in 1 year. Good clinical result and aesthetic. Conclusion. The form method provides a reduction of traumatic damage in the operative area due to the selective destructive effect on pigmented tissues and radical precision removal of giant pigment nevi with minimal damage to the underlying tissues while preserving the proximal areas of the skin appendages, which contributes to an active genital wound process with central epithelialization. The method of removal of various form provides a radical result, the absence of relapse, which helps to shorten the time and achieve good clinical and aesthetic results of the treatment. The method is perspective and can be used in children's patients in wide clinical practice. Thank you. this any excision on histological examination malignant parts we can this laser and ablastic this way the laser radiation on histomorphological examination.
So you mean that
we
there are some contraindications for this procedure? Yes?
Yes.
Okay. Another question?
Can you speak about the main mechanism of action? It's thermal or photothermal or
photothermal mechanism.
At which, why is it better than other ways?
That provides a predictable layer-by-layer removal of pigment tissues and minimize the damage to tissue structure subject to them, including the elements of the skin appendages located there, and this we can see on 90 days where impact zone is made by restored epidermis and evenly parallel collagen. The structure of the skin is preserved in included appendages. This provide a central epithelialization and we don't see scars and other complications.
If compare with heavy laser, it's better or it's other? If look on the spectra.
We proposed the selective absorption mainly melanin and oxyhemoglobin. The laser extended by water.
Okay. Thank you very much. Let's thank you again. Good job. And by Dr. Konopov from Oregon State University, application of optical spectroscopy in minimally invasive surgery.
Good afternoon, everyone. The topic of my talk is application of optical spectroscopy in minimally invasive surgery. Our research group is from City Oriel, and we have come to Biophotonics from Biomedical Engineering, and since 2018 we have been developing and introducing optical spectroscopy devices for minimally invasive surgery. And today I'll show you our results. Here's the outline of my talk. It includes the following sections: the introduction, the methods of optical spectroscopy, the results of clinical studies in abdominal surgery and gynecology surgeries, and conclusions. The aim of my talk is a review of the technologies developed based on optical spectroscopy for minimally invasive surgery. Minimally invasive surgery is a type of surgery that uses smaller incisions and reduces recovery time. But the surgeon has a limited vision field and doesn't have enough diagnostic information about the state of the organs. Minimally invasive surgery is applied in many fields of medicine. Our team has many of experience working with abdominal surgeons and gynecology surgeons. Optical spectroscopy can be combined with standard surgical instruments, and the questions is how can we introduce optical instruments, for example probes, during operations. Speaking of abdominal surgery, Sorry. А где указка? Speaking of abdominal surgery, the access to internal organs can be provided through tools for percutaneous needle biopsy and percutaneous biliary interventions. In case of gynecological surgery, we can use the laparoscopic port to insert optical probes. The optical spectroscopy methods allows us to get a lot of diagnostic information about biological tissues. Laser Doppler flowmetry is based on detection of laser radiation, which was backscattered and reflected from moving red blood cells, and following processing of the received signal. Laser Doppler flowmetry is used for assessing blood perfusion of tissue and study of mechanism of local blood flow regulation. Diffuse reflectance spectroscopy gives information on light absorption and scattering in tissues. The amount of absorptions depends on the tissue chemical composition, and scattering is related to the morphological structure of the tissue. Quantitative analysis of the reflected lights reveals functional state of biological tissue and allows to evaluate oxygenation, blood content, water content, etc. Fluorescence spectroscopy used for studies of tissue or cellular metabolism. Fluorescence spectroscopy application is based on differences in the intensity and spectral composition of the fluorescence of healthy and pathological tissues when excited by laser radiation in the UV or visible range of the spectrum. Quantitative analysis to the fluorescence spectra allows us to evaluate energy and lipid metabolism, biocomponents, and morphological changes. Fluorescence lifetime spectroscopy is a technique based on the differences in the exponential decay rate of the photon emissions of a fluorophore from a tissue. Fluorescence lifetime spectroscopy allows one to separate the contributions free and protein-bound NADH and study the redox homeostasis. These methods can be used separately and combined with each other in a multimodal approach. Raman spectroscopy is based on inelastic scattering of optical radiation when interacting with molecular bonds of tissue's components. The Raman signal allows us to identify the presence of certain molecules and to study chemical and intermolecular relations. Here, let's move to clinical examples of applying optical spectroscopy methods in minimally invasive surgery. Primary liver cancer is the sixth most diagnosed cancer and the third leading cause of cancer death worldwide. The final diagnosis is verified with histological and cytological analysis of a tissue sample obtained during percutaneous needle biopsy, which remains a gold standard for diagnosing liver cancer. Unfortunately, due to many factors, the percentage of non-diagnostic samples reaches 10 to 20% according to various data. The aim of this study was to develop and to test the possibilities of multimodal optical biopsy setups to differentiate liver cancer from normal parenchyma during percutaneous needle biopsy. The clinical studies were conducted at the Oral Regional Clinical Hospital. We used multimodal fluorescence spectroscopy and diffuse reflectance spectroscopy setup and a fine needle optical probe, including emitting and collecting fibers for measurements of fluorescence intensity and diffuse reflectance. The results of this study are shown on this slide. The liver fluorescence spectra experienced at redshift in wavelength and the peaks of tumor fluorescence maximum different from the peaks of intact liver. It can be caused by the increased presence of bile in the healthy tissues compared to the tumor. The oxygen saturation is the oxygen saturation of tumor is higher than that of intact liver. Possible explanation is that tumors are almost exclusively vascularized by the hepatic artery, whereas healthy liver is primarily supplied by the portal vein. Peak wavelength and oxygen saturation were used to synthesize the decision rules shown on this slide. The lowest level of error was obtained with a combination of peak fluorescence under blue excitation and oxygen saturation, or using all three parameters. Thereby, the combination of fluorescence spectroscopy and diffuse reflectance spectroscopy methods provide high sensitivity and specificity values to differentiate liver cancer from normal parenchyma. Next, I will present the results obtained using the fluorescence lifetime spectroscopy setup based on the time correlated single photon counting approach. In the experiment setup, a UV laser was used. We used a model of 2 exponential fluorescence decay. We used machine learning techniques to differentiate liver parenchyma and tumor, as well as classify different tumors. The machine learning approach applied to the fluorescence lifetime spectroscopy data provides high sensitivity and specificity values to differentiate liver cancer and liver parenchyma. Moreover, this approach allowed distinguishing between cancer types. Liver cancer, primary liver cancer, benign tumor, and 2 types metastasis. Obstructive jaundice is a specific type of jaundice caused by a blocked bile duct. Percutaneous transhepatic biliary drainage is a procedure in which a small flexible plastic tube is inserted through the skin into the liver in order to drain an obstructed bile duct system. Unfortunately, one of the complications of this procedure is the development of liver liver failure. Sorry. Currently, liver failure is evaluated indirectly, and there are no methods or specific diagnostic signs to assess this complication. We proposed to evaluate the metabolic status of the liver parenchyma by fluorescence spectroscopy. We used fluorescence spectroscopy channel of the multimodal setup that I talked about earlier. The analysis of obtained data was based on the deconvolution of the fluorescence spectra. We evaluate the contribution of known liver fluorophores to a total signal. The analyzed parameters included peak heights and area on the Gaussian curve. The results show a statistically significant increase in the contribution of curves reflecting NADH fluorescence, vitamin A, bilirubin, and flavins. This and the calculated redox ratio indicated the energy metabolism of the hepatocytes may have shifted to glycolysis due to hypoxia. These parameters can be used for future studies as promising diagnostic and prognostic markers for the cause of liver failure. In addition, the drainage system in the biliary tract of the liver allowed us to collect bile and study its optical properties by the Raman spectroscopy. After recording Raman spectra, we identify the major vibrational bands in the range 1000 to 1008 reciprocal centimeters. As bilirubin is one of the major components of bile, it was expected to present in the spectra. We are able to register spectra in patients without obstructive jaundice. We found that in patients with positive dynamics of the disease, the amplitude of bilirubin peaks in the Raman spectra reached the level of a patient without obstructive jaundice. On the contrary, in patients with negative dynamics of disease, peaks of bilirubin in the Raman spectra disappeared. The assessment of content of bilirubin and bile allows us to predict the recovery of the excretory function of the liver and adjust the treatment. Myomas. Myomas, benign monoclonal tumors of the smooth muscle cells of the myometrium. Myomas appear about 40% of women of reproductive age. Endometrial receptivity is a complex feature that provides the embryo with opportunity to attach, invade, and develop. Currently, all myomas more than 4 centimeters should be surgically removed. But there is no unequivocal opinion of how intramural myomas affect the receptivity of the endometrium. We used multimodal laser Doppler fluorometry and fluorescence spectroscopy setup and laparoscopic fiber optic probe. We recorded the laser Doppler fluorometry and fluorescence spectroscopy signals in the endometrium of the two groups. In group women with submucosal myomas and women with intramural myomas. We found that microcirculation in the endometrium of women with intramural myomas is higher, much higher than women with submucosal myomas. In addition, in a group of women with submucosal myomas, is an increase in the fluorescence signal with UV laser, which indirectly can indicate hypoxia. So the microcirculation of the endometrium in women with intramural fibroids is preserved, and perhaps the endometrial receptivity is not impaired. It is possible that the indications for surgical removal of intramural myomas need to be clarified. Optical spectroscopy methods provide information on metabolic processes, perfusion, morphological structure of biological tissues, and can be combined with standard surgical instruments. Multimodal approach seems to promise to increase the quality of diagnosis of tissue state and improve the quality of treatment. The instruments and technologies for minimally invasive surgery developed in the R&D Center of Biomedical Photonics allows us to differentiate healthy and tumor liver tissues, classify the types of liver cancer, evaluate the liver metabolism and excretory function in patients with obstructive jaundice, and possibly clarify indications for the removal of myomas in women of reproductive age. We thanks all patients who took part in clinical research and the Russian Science Foundation. This is our research group of biomedical engineers and surgeons. Thank you for your attention, and we invite colleagues to the conference in the oral in November. Thank you. Yeah, we have been sterilized, and we used free fibers and sterilized. Как по I mean, during procedure, when you make measurements, any blood doesn't come to the needle? When you enter the needle into the liver, does blood come to the needle? Yes. Unfortunately, this is we see but surgeon understand about this problem, and surgeon control with ultrasound and try пытаться избежать. Avoid, yes. Okay.
Thank you very much. It is well known that all processes in the human body are dynamic. Metabolic processes, in particular, tissue perfusion is very dynamic. And there are many control loops that make, that change the perfusion rate. So in this respect, the question is, how do you perform averaging of the results to ensure the repeatability?
We control tissue saturation in 3 to 5 points, and we evaluate mean saturation, то есть средняя, да, in liver and in tumor.
So you average in time?
No, about 1 minute. Thank you.
Let's thanks committee. Please, next speaker, Dr. Alexandrova from Prokhorov General Physics Institute. His report entitled as Feature Analysis of OCT Images for the Diagnosis of Brain Glioma.
Не видно еще презентацию.
Сейчас я поставлю.
Good afternoon, dear colleagues. Today I would like to present you our work, Future Analysis of OCT Images for the Diagnosis of Brain Glioma. So I divided my presentation on 4 parts. The first one is the problem of human brain glioma diagnosis. The second is principle of OCT. The third, method of analysis. And the last one is results. So the question is why intraoperative diagnosis of human brain tumors is so important, because glioma appears in almost 63% cases of human brain tumors and around 80% of malignant cases. Glioma has very poor prognosis, and the only key factor for the successful treatment is its total resection. It is very important to accurately identify the margins of tumor during the surgery, and also to classify tissue on malignant and healthy. So that is why nowadays many scientists and medics are looking for fast, non-invasive intraoperative methods for tumor visualization during their surgery. We use OCT, a light interference-based optical technique, which resolution is between optical microscopy and ultrasound methods, and penetration depth about 2 millimeters. Our research aimed at the study of the ability of OCT for the intraoperative diagnosis of human brain gliomas, and because OCT provides with strong imaging contrast and differences of scattering admission. And therefore, OCT technologies is widespread in a variety of medical fields, such as cardiology, gynecology, dermatology, and so on. In our study, we use an OCT system, OCT 1300Y from Nizhny Novgorod, with the central wavelength of 1.3 micrometers. So, we analyze human ex vivo samples accessed during the neurosurgical operations according to the initial diagnosis. Also, you can see on this slide the representative scans, OCT images for glioma of different grades according to the World Health Organization. During the measurements and during the transportation, all samples were covered with gelatin film in order to prevent hydration and dehydration of the samples. And after measurements, all samples were fixed in formalin and transported to histological examination. We also developed a data analysis procedure based on 2 optical parameters, the attenuation coefficient and standard deviation. But first of all, it was necessary to align the region of interest. That is why we cut our OCT image and filtered it with transfer function to avoid system distortion. So the first parameter is the attenuation coefficient, which analysis reflects mostly their structural properties of the subject, such as cell, nuclear density, and size. The second is standard deviation within a small region, about 150 micrometers, because it is the typical size of the human brain vessel. This parameter reflects mostly small heterogeneity of the tissue. So the next method was wavelet analysis. We used this method to obtain information from speckle noise, which always presents in OCT images. Using the wavelet transfer function, at the output we obtain diagonal coefficients, which are detailed coefficients, which are separated on vertical, horizontal, and diagonal. Using these values, we obtain the power of local brightness fluctuation depending on the decomposition level. So, because since the main purpose of our study is to differentiate intact tissue from glioma, from malignant tissue, it was necessary to find such method to separate these tissues. So we use linear discriminant analysis Fisher, and as you can see on this slide, this is results for both methods. This is for first and this is for second wavelet analysis method. You can see that we have really good separation for glioma from 1 to 3rd grades, and really bad, poor separation for glioblastoma, the 4th grade. And this is the main purpose, it's the main problem for surgeons, because glioblastoma is the most malignant type of tissue. So on this slide, you also can see the results, the values of sensitivity, and specificity, and precision. This is histograms of these values. This one is when we analyze two-dimensional space for our first method, optical parameters. This one and the third, this is also analysis of the two-dimensional space, but for the second method of different decomposition levels. So you also can see that the results not really good for glioblastoma, but we decided to resolve this problem, to solve it, and try to look at the four-dimensional space. So we use 4 parameters, the attenuation coefficient, the power of local brightness fluctuations, and their standard deviations. And you can see that we really increase the values of sensitivity, specificity, and precision for not only low-grade gliomas, first, second, and the third, but also for high, for glioblastoma. So I can say for sure that we made a next step to differentiate glioblastoma from intact tissues. So to sum up, we have demonstrated the application of 2 methods for differentiation intact human brain tissues and glioma of different grades, additionally for 4 grades. With the help of Fisher analysis, we have separated the intact tissues from glioblastomas and gliomas, and increased the values of sensitivity, specificity, and precision in the 4-dimensional space analysis. That's all. Yeah, I'll be glad to answer your questions.
Okay, a small question. You represented normalized intensity for your OCT signal.
Yes.
What's typical absolute value for contrast for your OCT signal?
Absolute.
In decibels.
Let's look. When we are talking about normalized, the maximum is 1 decibel, or well, yeah. If we are talking about normalized, yeah. It's in, well, maybe I didn't understand your question.
Relatively small.
Yeah, but we to.
Your images are much better since about 7 decibels.
Well, maybe I really didn't understand your question. You mean that how many scans, these scans we use to obtain, well, sorry, to obtain the normalized, or what?
What is the dynamical range when you are measuring an image? What is the dynamical range?
Of these scans, or what? Well, this is,
an OCT image.
well,
Dynamical range of the entire image. What is it?
So we have B scans, OCT images, 200 pixels on 400 primary pixels.
The value of the signal, not the size of the image, but the question is about the value of the signal.
Ah, okay. I can't say for sure now because we have only representative scans for normalized intensity. All scans we normalize to avoid distortion of system, and use only, well, with the highest level of 1. That's all I can say now for sure. But I have to mention that we do it with all scans, so we have differences for different type of gliomas. When we estimate these A scans, we obtain the attenuation coefficient, and they are different for different types of tissue. no, not in this work. In this work, only differentiate by intact tissue, cortex, and white matter, and glioma. Yes. Mm-hmm. Thank you for your question. I have to mention that we use not only gliomas of a human brain, but we also measured gliomas model by rats. And if I understand you right, we measure it from the whole brain and find the margin between glioma and intact tissues. But here, it is very difficult to do this with human brain. So only surgeons cut their area of glioma, and they say by initial diagnosis that it is glioma, the third, for example, or this is cortex. So we can look on OCT and find out even if it's true or not. We just believe them because that samples then transported to histological examination, and we confirm that diagnosis.
Okay, can speak again. Let's go to the final talk in this session. Dr. Plekhanov from Privolzhsky Research Medical University, please, and this talk is entitled as Assessment of Endometrial Tissue Morphology by Elastic Properties using Compression Optical Coherence Elastography.
Я включил у себя, да? Good afternoon, dear colleagues. Today I would like to present a talk called Assessment of Endometrial Tissue Morphology by Elastic Properties using Compressional Optical Coherence Elastography. Endometrial cancer is a common woman malignant pathology, surpassing lung and ovarian cancer in prevalence. Histological examination is required to diagnose and monitor the effectiveness of endometrial cancer treatment. But this requires an aspiration biopsy or separation or separated diagnostic curettage. Such procedures are highly traumatic and do not always provide high quality result. In addition, frequent use of such procedures can lead to chronic inflammatory reaction, thinning and fibrosis of endometrium, which in turn negatively affects woman's reproductive function. These facts indicate the search and development of new technologies for high precision, minimally invasive morphological assessment of endometrial tissue. Currently, MRI and ultrasound are used for instrumental examination of endometrial structure by a clinic. However, these technologies do not provide information about endometrial morphological structure at histological level. Widely used low traumatic hysteroscopy allow to evaluate visually of uterine cavity surface, but at the same time, using this method, it is impossible to study tissue morphology. It should be noted that in recent studies using transvaginal US elastography and OCT have demonstrated the ability to determine endometrial tissue morphology. Nevertheless, such methods lacked contrast to detect hyperplastic process and determine cancer subtype. Such experience allow us to assume the possibility of performing differential diagnosis of endometrial pathologies using compressional optical coherence elastography (COCE). Researchers from Australia and Great Britain for the first have demonstrated the ability of COCE to diagnose breast and prostate cancer by high stiffness values. Absolute stiffness values under standard compression conditions made it possible to distinguish between different morphological tissue structure. Thus, we carried out the first in vivo COC study in a tumor model during chemotherapy, study of the nonlinear elasticity of breast cancer tissue for each morphomolecular subtype, and study of central lymph nodes and colorectal cancer. This study aims to determine the capabilities of COC for diagnosing of human endometrial pathology based on differences in the elastic properties of tissue morphological components. A total of 28 endometrial tissue samples from postmenopausal patients after total hysterectomy were examined. Among the study's samples were uterine uterine tissue without pathologies, endometrial hyperplasia, low and high grade endometrial adenocarcinoma. The studies were carried out using a spectral multimodal optical coherence tomography in elastographic mode. After that, all tissue samples were taken for histological examination. Post-processed constructed COC and histological images were compared to determine the elastic properties of endometrial tissue morphological structures. In the used COC mode, the interframe strain were calculated by estimation actual gradient of the interframe phase variation using the vector method. Strain compression is applied by the output window of the OCE probe through the intermediate layer of linearly elastic translucent silicon. In this case, piece of silicon material acts as an optical stress sensor and allows you to quantify the elasticity of the tissue. The key feature of this technique is that it's possible to obtain stress-strain dependencies and the tangent Young's modulus or stiffness value for tissue using of reference silicon Young's modulus. Then using a special a special procedure based on local stress estimation, we can generate COC images corresponding to a preselected standardized pressure value. The elastic properties of normal postmenopausal endometrium, myometrium, hyperplastic endometrium, gland-like and non-glandular cancer were studied. No qualitative differences were found between morphological structures on OCT images, structural OCT images. However, on non-standardized maps of cumulative strains obtained at some intermediate compression, about 4 kilopascals of tissue samples. The differences in the cumulated deformation of endometrial morphological structure were observed. Next, the average stress-strain curves tangent Young's moduli for all 5 morphological structure as a function of strain and stress were plotted. During the stiffness stress curves analysis, a value of 3 kilopascals was chosen. At this stress value, the morphological structures differed from each other by stiffness. This is necessary for subsequent COC images construction. At this stress value, the COC images characterized the morphological structure as follows. Normal endometrium had low stiffness values. Myometrium was slightly stiffer. Hyperplastic endometrium was softer than normal endometrium. Gland-like and non-glandular cancer had high stiffness values. Next, we will take a closer look at the optical and elastic properties for each endometrial conditions. During normal postmenopausal endometrium examination, the boundary between endometrium and myometrium was not identified on structural OCT images. However, COC images were characterized by a layer structure with upper layer of low stiffness of endometrium and with bottom layer with slightly higher values, 200 to 400 kilopascals of myometrium. On structural OCT images of hyperplastic endometrium areas with disappearance of signal from incist endometrial cavities. Observed. Observed. Representative COC images were characterized by a homogeneous structure and reduced stiffness values about 50 kilopascals due to overgrown endometrial glands. Structural OCT images of low-grade endometrial adenocarcinoma were not significantly different from OCT images of normal endometrium. However, COC images show increased of stiffness values over 400 kilopascals of the gland-like cancer structure. In addition, this slide demonstrates the potential of COC to determine the topography and the boundaries of endometrial cancer, which could be used for targeted biopsy sampling in the future. No, finally, structural OCT images. No, last slide. Finally, structural OCT images of high-grade endometrial also were not significantly different from OCT images of low-grade endometrial cancer and normal endometrial. Nevertheless, COC images were characterized by a heterogeneous structure with increased stiffness values over 500 kilopascals of non-glandular cancer cells and average stiffness values 200 to 400 kilopascals of myometrical hordes for separating cancerous clusters. It's over. Я потратил все время. Спасибо.
Does anybody have questions? So thank you, Anton, for this nice presentation. And actually, my question is, how do you evaluate the perspective of transferences into clinics? So is it possible to construct an OCT probe that can analyze the endometrium with elastography also in vivo? Because I think this modification is quite large problem, so you cannot use it in vivo.
Thank you for interesting question. This technology is now realized on ex vivo postoperative samples by our colleagues from Institute of Applied Physics, Nizhny Novgorod, constructed transvaginal hysteroscopy-like probe from realization COC in clinic.
So you can control the compression and pressure of
control with absolutely with control compression on minimally strain to tissue, с минимальным оказанием компрессии.
Okay, let's go. Thank you, discussion.
here on the conference, and I want to present a talk entitled Gold Nanostars with Tunable Optical Properties for Biomedical Applications. Localized surface plasmon resonance is the main property of gold nanoparticles. Plasmon resonance is excited as a result of collective oscillations of free electrons under the action of incident light with a certain wavelength. The spectral position and amplitude of the plasmon resonance can be tuned by changing size, shape, and structure of the particles. Okay, there are many types of gold nanoparticles. Most common is the nanosphere, then nanoshell, nanorod, nanocluster, nanocage, and nanostar. Nanostars are a set of particles that have the following shape. One of the first papers about gold nanostars was published by Luis Liz-Marzan, a Spanish group. It's about synthesis of gold nanostars in colloid using polyvinyl pyrrolidone. Changing the PVP concentration, we can change the shape of nanoparticles and also tune optical properties. Next step is synthesis without surfactants. It is main because these particles are ready to be used in biotechnology, for example, for conjugation with biomolecules. Next step is synthesis of gold nanostars on seeds of various sizes. We use gold nanospheres of various diameters, and gold nanostars also can be synthesized with from small to larger diameter. It leads to tuning the properties from about 700 of nanometers to about 1000 of nanometers. Next, gold nanostars with small cores and thin spikes, also called nanoantennas, were synthesized at first in the lauryl sulfobutadiene solution, and the colloid has 3 plasmon peaks. The first correspond to nanospheres, second for nanostructures with small spikes, and the last for so-called real nanoantennas with long spikes. Next step in progress of synthesis of nanoantennas is using the tritone solution. Using this solution, the quality of samples is better, and using various concentration of ascorbic acid, we can obtain nanoantennas with tunable plasmon resonance and also with the shape which we want. Next step is changing concentration of ascorbic acid and tritonic store. Both concentrations can be, by changing this concentration, we can obtain the particle we want. Next step, silver nitrate. This reagent plays a very important role in the synthesis of nanantennas because without silver nitrate we will synthesize only spherical nanoparticles. Silver nitrate leads to formation of prolate structures. Here increase in silver nitrate leads to shift of plasma resonance to longer wavelengths. Next step is calculation of optical properties of gold nanantennas. So theoretically predicted 3 peaks correspond to 2 peaks in experiment. These places correspond to theoretical calculations. So here it is very useful that nanantennas has very expressed plasma peak about localized at about 2000 of nanometers. So it is close to the second penetration window. Now it is modern direction to work in the second penetration window. Our group also contribute in the modeling of properties of gold nanostars and nanantennas. We develop novel 2-component dielectric function for gold nanostars. So the main idea of this function is to use constant for bulk matter for nanostar core, and for spikes we used function which is corrected due to thickness of the spikes. Regarding biomedical application, we had collaborative research with our colleagues from Saratov State University. It is about to measure intracellular molecular composition of cells by surface-enhanced Raman sketching. We prepare the array of the layer of gold nanostars, and under the layer the cells were placed, and then due to sharp spikes of gold nanoparticles, the cells were porated, and the cell signal from intracellular composition was measured. Next, we also contribute in the synthetic protocols of gold nanantennas. At first, we added hydrochloric acid to the synthetic protocol, so it leads to with various concentration of hydrochloric acid. Also, the optical properties can tuned, and in this work also we change the concentration of seeds. You can see that with increase in seed concentration, plasma resonance of gold nanostars can be shifted to shortened wavelengths. Our recent work was also for biomedical applications. This report on this work was today morning by Professor Nikolai Khliptsov. It is about one-shot laser irradiation of various types of nanoparticles, for example, gold nanostars and nanoantennas. So we found the pulsed laser parameters with which nanoparticles turn into nanospheres. So it is meant for laser biomedical application because such transformation of nanoparticles leads to dramatic change in optical properties. So exchange of nanostars to nanospheres. And so to use laser, infrared laser is not effective after this transformation. Conclusions of my talk is gold nanostars have important advantages, expressed absorption and sketching at a given wavelength from a wide range from 650 to 2000 nanometers. Tuning is carried out by selecting synthesis parameters and remarkable morphological properties such as sharp spikes, which allow, for example, to perforate cells and measure cell signal inside cells. And due to the described advantages, they have wide potential for use in laser biomedical applications, such as surface-enhanced Raman sketching, photothermal therapy, bioimaging, and for this purpose, acceptable parameters of pulsed laser irradiation were determined. And I would like to acknowledge my colleagues, the head of our laboratory, Professor Khliptsov, and our team. Here is a photo from the table tennis tournament. And thank you for attention.
Actually, I have questions, if I may, if you allow. Short questions. First is, what is the stability of the suspensions of nano-stars and nano-antennas? Do they tend to aggregate? And if they do, what is the hydrodynamic strength of the aggregates?
Thank you. Very good question. Sure, stability is a poor moment of this particle, but you know, we need to, but it is not so bad. Just after synthesis, you have about 30 minutes to decide which molecules you will use to coat nanostars. And after that, they have enough stability. But the second moment is that you see that nanostars is bigger. Nanostars initial is bigger, yes, than nanoantennas. So they tend to aggregate. Because of big mass, they tend to slightly come to bottom slightly. But using slight ultrasonic bus, we can bring it alive. And nanoantennas have much more time to come to the bottom. And I think these particles, I like it much more because I think they are easy to work with.
Thank you. Another question. You pointed out a positive feature of nanostars that they can puncture the cells, and this allows you to make source measurements. But presumably, if you intend to use them for
you know, we use these particles not for use by themselves, but we use it, they to create composites. For example, to coat with shell, with drug delivery, with something like that. And these particles are used as for photothermal therapy, as heater in this structure. But if we want to check cell signal, for example, yes, inside the bloodstream or something else, it's interesting question, yes. Thank you.
Thank you.
I have a question. So here in this presentation, you show that laser can induce some modification of the nanostar, right? So what is the mechanism behind it, and is it like stable enough? Because 65 millijoule per centimeter square is quite small.
You know, it is calculated for nanosecond pulse laser. So for such a laser, it is few times lower than the level which is possible to use for human. I think it is about 5 times lower than this limit. So it is not a very small limit, you know. And sometimes you can use it to melt particles for some applications. Maybe for more effective destroy some tumors or something like that. You can use some strategy for this purpose.
And what is mechanism behind the laser?
Mechanism is heating.
It's just heating?
Yes.
And it melts?
Yes, it is gold and it is a lot of atoms are outside on the surface.
Okay, thank you very much.
No question? Let's again, speaker again.
Thank you.
And the next talk will be a little bit, I don't know, Dr. Chernyshov. Yeah, sorry. It's from National Research State University. And the talk will be treatment of neoplasms and integrated nanoparticles. It can be required iron.
Какой папки? 1809, да?
And 170 nanometer radiation. Please have 30 minutes and please leave a couple of minutes for question, yes?
Okay, I understood. Okay, very well. So, thank you for introduction me. Now today I will tell about first stage of our investigation, treatment of neoplasm using these dielectric nanoparticles. Okay. So, first of all, a little background. There are some publications reported about appearance white brown-band emission in dielectric nanoparticles, highly doped by rare earth ions, when these particles are excited by intense laser radiation to the absorption band of these ions. And we studied ytterbium doped particles with different structures and confirmed that this white emission is thermal emission, and we suppose the mechanism responsible for this thermal emission in dielectric particles. This mechanism includes nonlinear interaction between rare earth ions and defects. Following interaction electrons in conductive band with lattice. We studied different compounds with different ions and different excitation, and we concluded that most important factors for compounds is band gap value and presence of defects. And we concluded that particles, zirconia-based particles, is more applicable for obtaining white light emission and heating. So we supposed that this heating effect can be useful for any application. For example, for medical application, we can enhance thermal effect of laser action to the biological tissue for non-contact mode of action. We completed preliminary experiment, in vivo experiment, and showed that we have intense injury when we use nanoparticles. So heating is higher than without nanoparticles. From in vitro experiment, we choose most appropriate compounds. It is zirconia-based compounds with ytterbium ions, with high concentration of ytterbium, and for laser excitation of near-infrared spectrum. And the aim of current report is to study the possibility of using these particles for removing neoplasm. So we have seen that zirconia particles with cubic structure, and the size of the particles is about 30 nanometers. The emission spectra of these particles are typical as for previous particles. This is thermal emission. We can see corrected spectra or uncorrected spectra. This is spectra in shape is close to spectra of emission of gray body. And also this emission are not linear. For in vivo experiments, we used mice with melanoma, with this type of tumor. And on the 7th day after tumor implantation, animals were divided randomly into 4 groups. First group was negative control without treatment. Group number 2 received intratumorally suspension of nanoparticles. Group number 3 received superficial suspension to the tumor, and group number 4, that is positive control. Groups number 4, 3, and 2 also received laser irradiation, and we have controlled surface temperature 60 degrees for group number 2 and number 4, and 120 degrees for group number 3. So, and what we have obtained. So, first of all, we controlled and compared temperatures using nanoparticles and without nanoparticles in different layers of biological tissue. And we see that using nanoparticles, we have higher temperatures on surface. In deeper layers, we have less temperature than without particles. It may be due to high absorption of laser radiation by particles. So, also, we compare survival of animals for different groups. For group positive control, we have less survival is equal to 24 days. For negative control, survival was 21 days, and higher survival we have for group number 2 and 3 with particles. So, and we can see that 50% of 50% of animals in both groups live, and median survival for group with surface application was less than for intertumoral application. Also, we have compared volume of tumor for different groups, and we can see that for groups with using of nanoparticles, tumor size was less. And for other groups, we have higher tumor size, and for group for positive control with only laser irradiation, we have stimulation of true tumor growth. And also we calculated tumor growth inhibition rate, and in third day after therapy, we see that for positive control it was negative. It may be due to stimulation of tumor growth, and we can see that for groups with particles we have high TGI index. On 13th day from therapy, we see that higher TGI value we have for group that received intertumoral particles. And also higher value we have for group with surface application. So we can conclude that using particle has some anti-tumor effect, but we need to study mechanism of action, mechanism of cytotoxicity of these nanoparticles. We need to study tumors, different types and different ages. So, and also we can conclude that more effective therapeutic effect achieved with intertumoral administration. So, thank you for attention. Variability, you mean okay. With laser radiation, we suppose that stimulation of tumor growth, and we have appropriate data in scientific literature according to this. That melanoma is very aggressive tumor, and any injection can stimulate it. Okay. We just a moment. We try to choose those for infrared radiation according to literature data. So this value is according to literature. And for for first experiment, we choose this dose. Firstly, we completed in vitro experiment, measure temperatures, compare these temperatures, and choose appropriate concentration of nanoparticles. And we control the surface temperature because we irradiate this group twice. So we injected nanoparticles, irradiate, wait, and after that irradiate once again. So in this case, we irradiate without any injections, additional injection.
What about systemic injection?
No, we did not make it.
Any questions? I have two very short questions. You mentioned temperature control. Did you mean local temperature or global temperature?
Temperature in surface, in point. In colloids, point temperature, high temperature. We use thermal imager for this. Here, in this experiment, no?
Could you please show us plots?
This? No, this is not colloids. It's in experimental mouses. This temperature was controlled by a thermocouple. But we choose some mouses for measurement temperature, but we did not use these mouses in other experiments because...
Of tissue.
Yes, it's tissue.
And second one is, which type of laser do you use? CV or pulse?
CV. This effect, this interesting heating effect, we can see only in CV laser mode and high intensity laser radiation.
Any questions? No questions. Thank you again.
Thank you.
The next talk will be presented by Vassily Novikov. Raman study of biodegradable materials.
Yes. Good afternoon, dear colleagues. My name is Vassily Novikov. I'll present you the work named Raman study of biodegradable poly-L-lactate polymers caprolactone materials. The introduction. These materials is used as medical materials, for example, for implants, scaffolds, and nanocarries for drug delivery. And it is well-known fact that the different application need different chemical and physical properties. And these properties can be variable by changing the composition of the polymers and, for example, crystallinity degree. When you create such materials, you have to control them during the production, and also during, for example, while they waiting for time they will use. So such method we suggest such method as Raman spectroscopy, because this is not it's in vivo method, and you can use this material after you after you checked it by Raman spectroscopy. It is well known that the Raman spectra of such materials is depend on structure of polylactate and other polymers included in it. And but there is a few works which explain how it can be used to control the crystallinity degree and polymers composition. And I'll show you the spectral regions which can be used to control such parameters. First of all, I'll show you samples. So we use neat polylactate and polycaprolactone and their polymers with different crystallinity degree and different composition. So as you can see, we use as crystal materials and also amorphous. The experimental setup you can see on the screen. So we used Raman spectrometer Centera 2 with a variable spectral resolution, wavelength, objective, and we use geometry of scattering with 180 degrees. First, we should choose spectral resolution and wavelength. Here you can see a spectra which was recorded using 532 nanometers excitation and with different spectral resolution. And as you can see on the central spectra with the spectral resolution of 4 reverse centimeters, you can't see the changes which become with different crystallinity degree. And by using spectral resolution of 1.5 reverse centimeters, you can see that we can resolve several lines on the central spectrum. Also, we recorded spectra using 785 nanometers. We can see the same not spectra, but the same properties. So we can't reverse or resolve lines with the spectral resolution of 4 reverse centimeters, and we can do it using 1.5 reverse centimeters. But later we decided to use just 785 nanometers excitation because it have lower background and we don't have such thing as we call ripples, so it is some effect related to the spectrometer when you use 532 nanometers excitation. So later, we will use 785 nanometers excitation and spectral resolution of 1.5 reverse centimeters. Here you can see Raman spectra of different samples with different crystallinity degree on the left and different composition of copolymers. And on the right spectra you can see spectra with different composition, but all of them are amorphous samples. And you should first look at this part of spectra. This part of spectra was the authors of some works in the literature told us that this part of spectra can be used to determine the crystallinity degree of copolymers. But when we look more carefully, we can see that this line contain some effect that so that the spectra not only determine the crystallinity degree but also the composition. So you can't control changes in the spectra and use it for determination of crystallinity degree because of these two facts. So let's go back to the whole spectra, and now we will have a look on the left side of spectra. And here I should say that as you can see, the all spectra with polylactide subpolymer, which is lower than PCl, is polycaprolactone polymer. They looks the same because the polylactide spectra is rather more intensive. So the changes in the spectra when you add polycaprolactone is not so strong, but there are some part of spectra on the left, as you can see, which depends on the on the composition not so strongly, but it depends firstly on the crystallinity degree, and we can use it as the determination of the crystallinity degree by Raman spectra. So we choose the line which is most strong, depends on crystallinity degree. It is line near 400 reverse centimeters, and we use the ratio of intensity of this line to intensity of polylactide line, which is near the 874 reverse centimeters. And you can see that it is maybe not a great straight line, but you can really use it as a crystallinity degree determination by Raman spectra. So the next spectral region is high wave numbers, and here we can see also that there is not so much changes in crystalline and amorphous samples with different compositions. Okay, let's move on. Another very important problem is to determine the component content. And we find that this spectral region, as you can see on the screen, is sensitive to component contents. And you also can use lines which is determine exactly one of the polymer as a Raman method to determine the composition of subpolymers. Here you can see the ratio of different bands, which makes it possible to determine the polylactide molar content in your samples. So the main results that we found regions which is sensitive to crystallinity degree of the samples, and regions which we can use to determine the composition of the samples. Also, we showed that spectral region near 1,700 reverse centimeters is not applicable to use it as a crystallinity degree determination. And so we showed that it can be applicable method for the medical problems for determination of component content and crystallinity degree in some medical things. Sorry. So thank you for your attention. I will be glad to answer your questions.
Thank you for your presentation. I would like to ask, could you please go back to the spectrum where next here.
This.
I do not see much difference, but maybe in your science more clear. I see that on the left side, on the left graph, so mostly that we can say that there is presence of polylactide.
Yes.
Not so much change, I suppose. And how can we explain that? The second question is, how did you control the crystallinity?
The first question. So you're right. There is no so strong difference between the spectra, but if you take the ratio of the peak intensities in the spectra, it is enough to say which composition content you have. It's because on the left, yes, on the right, in amorphous state is no difference. But when you have a crystal material, it is possible to use it to determine composition.
To continue this, how many peaks did you fit?
What?
How many peaks? because here, for example, at 35, we see that the combination between the polylactic and polycaprol. You see that the peak at 39, 14.
What do you mean peak? It's
The peak
points.
intensity.
Peak intense.
How many peaks did you fit to know the peak intensities?
We just recorded several spectra, and then we sum them, summarize, and so you have just one spectra from several points of the.
I mean the peak intensity that you.
You just take spectra and take this one point and another one point, because you have one sample with some crystallinity degree, so with one composition.
So you didn't do the econvolution, right?
No, it's just peak intensities.
Very short question. Very interesting and precise data, but for pure sample, what about complex environment?
It's, I think, the next step of our work, because we just start in the previous year, and the first step is just to take neat materials and in which we know the degree, crystallinity degree and composition, and then we will use more complex objects.
Thank you again.
Thank you.
The next speaker will be iron signal particles coated with photosynthesizer for phototherapy. Experimental study of local intracellular heating. Very interesting talk.
Hello everyone, nice to see you all. Thank you for introduction me. My talk about iron oxide nanoparticles and intracellular heating experimental study. First of all, iron oxide nanoparticles with magnetic properties are very promising because they then can be used in MRI and also for hyperthermia. For example, it can be conjugated with photosensitizer and applied to combine photo and magnetic therapy. Our interest to these materials arose a few years ago when we tried to use iron oxide nanoparticles as drug cargo, as photosensitizer cargo. But we did not can observe any fluorescence enhanced, but we observe in other also very interesting effects. I try to start video. One moment. Can you start video?
Видео хотите?
Да.
Прикольно. Наверное, не получится.
Yes, problem, typical problem with videos.
Sorry. Sorry for without video. Oh, this small video seems that this time lapse for cell with scanning electron scanning laser microscopy, and during laser scanning you can saw tiny spots with high fluorescent intensity, and this spot arise inside nanoparticles aggregates. We try to estimate temperature of this irradiate from particle, and measure spectrum of irradiation, and saw that the spectrum of these spots was like a black body irradiation, and maxima of this light was near 600 nanometers, and this correspond to 5,000 degree. This was amazing, very high temperature in very tiny pixel, in a very tiny spot. Of course, we estimate power density during laser scanning in confocal microscopy with 1% of laser that we applied. It was near 200 kilowatt per centimeter square, but the duration of laser scanning was only a few microsecond, in order 1 microsecond, and this power density during 1 microsecond hit our aggregates to 5,000 degree watt, and we decide more precisely investigate this effect. We apply modeling. The finite difference time domain method, its implementation in COMSOL multiphysics was used. Step-by-step procedure, inclusion calculation of absorption and scattering cross-section for iron oxide nanoparticles with different shapes and size. And after optical properties calculation, we apply it to heat transfer. We use parameters, standard parameters from for ferrum 2O3 oxide, ferrum 3O4 oxide, thermal conductivity, density, and refractive index and extinction coefficient. And apply this modeling, we calculate extinction and absorption and scattering cross sections for iron oxide particles with different shapes. Of course, first our observation was for aggregates of nanoparticles, and when cell uptake particle, uptake ferrum oxide nanoparticles, it accumulated inside a small volume in endosome, in lysosome, and in vivo these single particles complain ensemble or array, and we because of this we also modeling optical properties for array of several particles. And after this, when we calculate how effective particle and its array interact with light, we calculate heating temperature increasing for particles. On this graph, you can see that particles with size 15 nanometers and particles with size 35 nanometers, and different forms, cubes, spheres, and nanorods, and different types of iron oxide, ferrum 3, or 4 oxide, and ferrum 2 or 3 oxide. And from this dependence, it was estimated that heating higher for cubic nanoparticles and for wavelength of heating 420 nanometer, the iron oxide ferrum 203 better than ferrum 304. The next step, this is a big table with all calculated parameters, and in this temperature increasing, you can see that for arrays comprised from 5x5, x3 nanoparticles, the temperature rise more than 150 degree, and for 2 wavelength, some value was enough to heated array of particle. But when particles in water, for example, in media with high thermal conductivity, there are heat dissipants appear, and if we apply this parameter in model, our simulation, the total heating was only 3 degree. But in cells, not only water inside, and in small volume inside lysosomes, for example, this is lipid bilayer, and thermal conductivity for lipid bilayer another, and the heating parameter will be better. The next step, experimental study. We very thankful for a colleague from MISIS, Maxim Abakumov group, that they give us a lot of variant of shapes of iron oxide nanoparticles. It was spheres, rods, cubic, octopods, and a lot of another. And we measure temperature in vitro. For measure temperature, we choose method lifetime fluorescence thermometry, and we use rhodamin B, calibrated with our system Becker-Hickel film model on confocal microscopy. And after this, measure water colloids for these nanoparticles, and there was practically no heating in colloids. But when we place nanoparticles in cells and calibrate rhodamine intensity for cell system. Rhodamine accumulates in mitochondria and nanoparticles in lysosome. And after this, we with film analysis separate hot zones with short fluorescence of rhodamine. We get such results. This is a graph with fluorescence lifetime. This is calibration for cells line when we heated cells from 20 to 60 degree. And this is hot spots for nanoparticles inside cells. And measured the same way. The temperature that we measure was more than 100 degree. And this is proof for temperature can rise a very high value during laser scanning in cells, and during laser local laser hyperthermia with ferromoxide nanoparticles, the local temperature will more higher than the total for all sample. And this high temperature can start cellular process of programmed death, not only apoptotic, but a lot of another programmed cell deaths. That's for future perspective for cancer therapy to investigate how temperature influence to programmed cell death, for example. Thank you for your attention. This is a summary for calculation and for cells in vitro measurements.
Thank you, speaker. Thank you very much for the presentation. And actually, I have a question regarding the simulation of heating of array of particles. So you demonstrated us that you have quite even distribution of the particles in the volume there. So, and when we are working with living objects, we can expect that the distribution of particle can be random. So, will this affect on the heating of the particle array? Could you please comment on this?
We try to simulate not very large arrays of particles, but I screen a lot of publication with transmission electron microscopy of accumulation ferromoxide nanoparticles inside cells, and we try to make our model closer to quantity of particles inside one lysosome.
No. I mean that in your simulations, the particles are distributed at equal distances. Have you tried another configurations? Will this affect?
The size between particles. Of course, we try a different distance in array between particles also, and we choose this size that I show because also we estimate a layer of polymer of particles and a distance between two particles. Yeah, maybe.
Thank you for the presentation. You mentioned that your particles accumulate with the lysosomes where pH is very low. Did you check for pH dependence of the light
pH. We don't investigate that this moment. Mhm. Yes. At, mhm. At first, we placed colloids in different pH, but optical property does not change for our particles in different pH, and in our model we don't make this difference any pH. Yes. Mm, I hope that 3 hours after incubation in cells, particles still stable. Yes, I hope.
Short question. Thank you, Nastya. In your summary, you point out that nanoparticle assemblies are heated better than single nanoparticles. Well, actually, aggregation of nanoparticles is, in most cases, considered as a negative factor. So, is there any reasonable limit for the size of the aggregate? Or the larger, the better?
The larger, the better.
Huh? Or it is just a fact of modeling?
For heating, the larger the better, but this is a result for our modeling parameters.
I think there are a lot of very interesting questions concerning, for example, 150 temperature, which evaporation of water inside it. So let's continue. We go to break. Thank you, Nastya, again. And the next presentation will be done by Denis Murashko. Formation of composite nanostructures by multiphoton lithography for biomedical applications. Institute of Biomedical Systems. Denis, you have 15 minutes. Please.
Okay. Good day, dear colleagues. The two-photon polymerization is a technology of the additive manufacturing capable for the construction of the 3D micro and nanostructures. As indicated by its name, the resins polymerized by this technology absorbs two photons at longer wavelength, usually in the near-infrared spectral region. The two-photon process has mainly two advantages over the single-photon process that is used in the conventional rapid prototyping. The first one is that due to the most of the polymers has negligible linear absorption in the near-infrared region, and therefore the laser beam can penetrate deeply into the material and initiate the process of the polymerization without causing any photochemical reactions outside of the focal volume of the beam. And the second one is that the quadratic dependence of the polymerization rate on the light intensity enables for us the 3D spatial resolution and also the far better accuracy compared to the single photon polymerization. By using this technology, we can create the biomedical devices. And for example, I show you the artificial skeletal system. And the skeletal part was created here by using the polymer SU8 with the vacancy at the joint for the bovine serum albumin as a muscle. And in this example, the device was affected by the changing in the pH value of this surrounding. So if we change the pH value from the 5 to 13, you can see that this device has a closed and open state. And in our investigations, we were trying to create this similar device, but not affected by the pH changing, but by the electrical field. And for these purposes, we were using the carbon nanotubes, which were incorporated into the BSA, bovine serum albumin matrix. Why we choose the bovine serum albumin is because of its commercial availability and also for its known properties such as elasticity or its degradation rate. And for the preparation of our nanostructure, we were using the aqueous dispersions that were prepared by a process shown on this picture, where we were weighing our components and then mixing them, and after that they had the ultrasonic treatment. The ultrasonic treatment were used to prevent the fast aggregation of the bovine serum albumin and prevent the denaturation. So the next step for our process of two-photon polymerization was to find the photoinitiator. In this case, we selected 3 Deweys to be the photoinitiator. That was the methylene blue, rose bengal, and riboflavin. And we tested the transparency in the mostly in the region from 350 nanometers to 400 nanometers. And for us, the lower was the transparency, the better. So as a result, we found out that the riboflavin was the best candidate in our case. And so we, in our following experiments, we added only him in our dispersions. The experimental setup was including the femtosecond titan sapphire laser with the tunable wavelength. And to tune the power of irradiation, we were using the optical mechanical attenuator with the Glan prism. The samples itself was placed on the mechanized table, and the laser pulses were reaching our experimental object by using the mirroring system and the objective of the microscope. So the parameters of the laser irradiation shown in this table, and the initial beam had the Gaussian profile. For the mechanized table, we created the macros which followed it by the square trajectory. And to perform the two-photon polymerization, we created the polydimethyl siloxane wells that was attached to the glass substrate. And following which, we added solutions to these wells and placed under the objective of microscope and initiated the laser irradiation. It should be noted that there was no movement in z-axis, so the variations in the high are due to the non-planar substrate surface. The results obtained the results that we obtained were investigated by using the SEM and optical microscopy, and the study showed that our structure was in the micrometer range. And also we following studied its mechanical properties and conductive properties. To study its mechanical properties, we used the nano hardness tester nanoscan 4D compact with the Berkovich pyramid. As for the conductive properties, we used the Van der Pau method. And the results showed that the addition of the carbon nanotubes into our experimental object led to the increasing in the Young's modulus and also in hardness. And as for the conductivity, it allowed, it ensured that in our structure was conductive. So the results of our investigation is following that the transmission coefficient of aqueous dispersions with different photoinitiators were investigated. We presented the method of two-photon laser formation of composite nanostructures. We investigated their sizes and investigated their mechanical and conductive properties. Thank you for your attention. I'm ready to answer your questions.
Thank you.
Thank you for very interesting talk. You studied mechanical properties, optical properties. Can you say some words about biosafety and the biocompatibility of your materials?
I can say that bovine serum albumin is commonly used in the biomedical devices included, and as for the carbon nanotubes that we used here, is mostly dependent of the type of the carbon nanotubes and also of its concentration. But in our case, the concentration was low, pretty low, that we can say that it was compatible, although the experiments is still in plans, I would say. Yes, please.
So what is your nanostructure after laser iteration? So that is combined with graphene and carbon nanotube, or?
It's combined it's the combination of the BSA structure with incorporated in it of the carbon nanotubes, which in our following experiments we're planning to use in the flexible electronics devices.
Okay, so BSA is not modified
Well, it was polymerized by the two-photon.
Polymerized?
Yeah, yes.
Thank you very much.
So, thank you, speaker again.
Thank you.
Картинки не работают, я сюда поставлю? Да. Не знаю.
В смысле? А вот здесь не работает?
Да-да-да.
А куда здесь? Там у меня есть, да?
Я уже загружала.
Ладно. Нет, у тебя отсюда будет сейчас PDF или отсюда?
Ну, картинку здесь, сейчас, минутку. Я проверю еще раз. Видите, они не грузят. Здесь. Я поэтому...
А вот сейчас, слушай, наверное, ссылки не закинул, не файлы массовки, видишь?
Нет, это было...
Понятно.
Египка. Да.
Так, посмотри, у нас получается, отсюда видишь, она может так подать, на картинке можешь шнурок перетыкать придется. Ты что?
А может...
Параллельно не получится.
А если подключим сразу к моему ноутбуку?
Давай, отсюда тебе презентация готова своя?
Да-да-да.
Ну давай так сделаем.
Если нужно.
Все, отогрей.
Это правда? Так, сейчас попробуем.
Так, аппарат так, шнурочку.
Ага. Вот так. Машу еще мышку. Наверное, с этой стороны.
Не торопись, потом.
Good afternoon, dear colleagues. My name is Gulia Bikpaeva, and I'm PhD student. Oh, PhD student at St. Petersburg State University. My talk today is hybrids of carbon quantum dots and photoswitchable phosphonates, peculiarities of optical and biological properties. Rapid development of pharmacology generates several breakthrough directions, one of which is photopharmacology. Pharmacology is characterized by the general effect of the drug on the body as a whole. And photopharmacology provides localized effects in space and time. Nowadays, the main players of photopharmacology are photoswitch and pharmacopes that change biological activity because of light radiation. Photopharmacological agents are used to treat a number of diseases, such as Alzheimer's disease. Photoswitch is compound changing structural geometry and chemical properties under the optical radiation. As photoswitch are usually used azobenzenes, dioletanes, and other. Pharmacophones possess a particular biological interaction with substrate. Various antibiotics for the treatment of skin disease, Alzheimer's disease, and others have been demonstrated as pharmacophore. However, pharmacophones often lose of effectiveness after conjugation with photoswitch. In addition, a limiting factor is time-consuming procedure for searching for photoswitch and pharmaco compounds with biological activity. And treatment of local disease, localization of the impact zone. In this regard, the relevance of the development of compounds with photomodulate bioactivity becomes critical for photopharmacology progress. The latter determines the interest in the development of compounds with photomodulate biological activity. Earlier, we have demonstrated a family of phosphonates, arylaminomalanates, a new organophosphor compounds. The chemical structure of this molecule is presented on the slide. It was found that after laser radiation, the color of the solution changed. In addition, the optical properties of these compounds change under the influence of laser radiation. We found that arylaminomalanates is a good inhibitor of cholinesterase enzymes. Cholinesterase is an enzyme necessary for the normal functioning of the nervous systems. Two types of cholinesterase are more common of the human body: acetylcholinesterase, which is contained or is synapses and red blood cells and predominates in the brain. The increased content of butyrylcholinesterase is characteristic of patients with Alzheimer's disease. In our work, we investigated the change in the biological activity and the solution before and after laser exposure. As a biological activity, we measured the inhibition of butyrylcholinesterase. After laser exposure, a significant fourfold change in inhibition is observed. So we have found that the result irradiation, absorption spectra, and inhibition butyrylcholinesterase are changed. In accordance to DFT calculation, laser radiation results in change of molecule structure. This conformational change are connected with rotation of phosphonate group. A change in the spatial structure of the molecule leads to change in the interaction with the biological target. Thus, at this stage, we have a photoswitchable and biological active compound. It is important to note that the principle of photopharmacology is of particular importance for the treatment of localized disease affecting certain organs. The solution to the problem of visualizing to the distribution of the in-body disease can be implemented by creating hybrid nanomaterials. In such hybrids, the visualization function is performed by luminescent nanoparticles, and the drug function is provided by a biological active substance deposit on the surface of nanoparticles. Carbon quantum dots can be used as luminescent nanoparticles. Carbon quantum dots are small, highly soluble in water, have photostable intense photoluminescence, and they are biocompatible and non-toxic. The carbon quantum dots surface can be easily functionalized to solve specific problems. To study the effect of components, conjugation of phenol photopharmacological properties, we prepared several samples based on phosphonate and carbon quantum dots mix, hybrid 1 and hybrid 4. Mix was prepared as a result of adding phosphonate powder to the carbon dots suspension in isopropanol. Hybrid 1 was obtained by sample mix stirring with magnetic stir for 1 hole. Hybrid 4 was obtained as a result of 4-hour stirring. The optical and biological properties of the obtained compounds were studied. According to the absorption spectra, hybrids are obtained. The characteristic bands of individual components are viewed on the absorption spectrum. When studying the luminescence of this system, in terms of that luminescent intensity for hybrids is less original quantum dots and the mix. The next step in the study was laser radiation of previously obtained samples. Laser radiation of the samples was performed with laser wavelengths 266 nanometer, power 120 milliwatt, with focused laser beam in quartz cells. Laser radiation time was 30 minutes in all the experiments. After laser radiation, significant change we found on the optical, biological, and luminescent properties of the hybrids. In the case of irradiation of hybrids, the luminescent properties change greatly. There is a decrease in the luminescent intensity and in particular or a shift on the spectra to the red region is observed. In addition, it was found that the lifetime of quantum dot change for irradiation hybrids. It was found that laser radiation has a significant effect of the biological activity of compounds, the experiments. It has been found that nanohybrids demonstrate increase in inhibition of butyrylcholinesterase from 38% to 100% after laser radiation. The main results of the study of biological activity are presented in the slide. Hybrids allow you to visualize the area of impact due to quantum dots. And this can be detected even against the background of autoluminescence of biological objects. In addition, irradiated and non-irradiated hybrids differ of the lifetime of luminescence. In conclusion, I want to say that we resolved that hybrids have a number of important properties for photopharmacology. Bioactivity towards butyrylcholinesterase inhibition and inhibition change as a result of laser radiation. Luminescence registered against in the autoluminescent background of biological tissues. Luminescent kinetic as an indicator of state of biological activity of hybrids. Thank you for your attention. Can you repeat, please? Может быть... Да, можно.
потому что, во-первых, вредно, а во-вторых, глубоко нельзя?
У нас была выбрана эта длина волны, потому что, во-первых, по-моему, эта длина волны проникает глубоко в кожные ткани, точнее,
Кожные ткани глубоко? Мы бы так
точнее,
не рассуждали. Наоборот, как раз у кожи основная функция – это защита от ультрафиолета. Ну, одна из ультрафиолета.
Да, смотрите, наши наноагенты, которые мы получаем, рассчитаны на то, чтобы работать именно на поверхности кожи, а не проникать глубоко в ткани. Вот, поэтому была выбрана эта длина волны.
Но это все равно вредно. Облучение кожи ультрафиолетовым излучением на коже вредно.
Ну, конечно, но мы при этом используем мощность лазера, если вы обратили внимание, это 120 милливатт, и зачастую это еще меньше. То есть это настолько маленькая плотность мощности, что на самом деле я думаю, что они приносят столько вреда.
Какое пятно? 120 милливатт это мощность, а плотность мощности какая?
Если я не ошибаюсь, то это где-то 0,5 сантиметров на квадратных сантиметров.
Вы размазываете по половине квадрата. Ну, может быть, но на
Да.
самом деле для меня это не выглядит очень безопасно.
Но на самом деле это расфокусированное пятно, это не вот концентрированный объем в одну точку.
Ладно, спасибо.
I have a question. Why do you call your materials hybrid, not just a mixture of your carbon quantum dot and the material you have? What is the difference?
Есть разница между смесью или у вас какой-то гибрид действительно получился? Или просто смесь?
Thank you for your attention. We assume that this special interaction of phosphonate and carbon quantum dots. At this moment, we are continuing to the study compound.
Well, thank you, speaker. I thank all audience.
Я просто
Да, все.
А можете убрать, иначе я выдерну. Спасибо.
Так.
Спасибо.
Пожалуйста. Так, значит, мы с вами договорились на завтрашний.
Все, да. Утро во сколько у нас начинается?
Нет, ну там пленаре там в 9 там начинается.
Ну, то есть утреннюю сессию мы откатываем и потом начинаем работать с ребятами с Китая.
Первый спикер будет это руководитель всей китайской делегации.
Да, ну, здесь дело не должно понять по времени. То есть у нас первая сессия здесь местная будет, потом между ним будет пауза, и мы закидываем китайцам, работаем с китайцем на, как это правильно сказать? Или прям с утра?
То
есть во сколько сначала-то еще будет? Давайте.